Hello, thank you for joining me in this presentation. My name is Raresh Stefan Alecu, and I'm here to present my research work on the topic of expressive brass wind modeling, which was supported by the Nordic SMC network and by Audio Modeling, a software development company based in Italy specialized in production of virtual expressive acoustic musical instruments. This project, titled Embouchure Interaction Model for Brass Instruments, was done together with Stefania Serafin and Sylvain Willemsen from Aalborg University Copenhagen, and with Emanuele Paravicini and Stefano Lucato from Audio Modeling. In 1973, John Chowning, one of the leading developers at Stanford University, innovated the technique of emulating complex audio spectra using frequency modulation synthesis. One of the benchmarks for testing the quality of this synthesis method was to emulate brass-like tones. Before and since then, emulating brass sound has been considered one of the more difficult benchmarks for audio synthesis testing, especially in the field of physical modeling. This is due to the human factor, which plays an important role in shaping the sound of the brass instrument. More exactly, it's because of the nonlinear characteristics of the brass player's lips and mouth muscles, which form the embouchure component of the instrument. While many state-of-the-art approaches in brass wind physical modeling have pushed the quality of the timbre to a higher level, its potential as an actual instrument for expressive sound synthesis is still far from being achieved. With the advent of hardware platforms that encourage expressive interaction with virtual instruments, like the Rowley Seaboard, there's a need in designing physical models with expressive control. This means that details lost to oversimplification of the interaction with these models need to be recaptured in some capacity. Thus, the focus of this project is on modeling the embouchure of the brass wind instrument by taking the simplified state-of-the-art approach and adapting it to consider the influence of additional aerodynamic forces. The sound of a brass instrument is generated from the airflow that passes through the brass tube resonator, which is modulated by the vibrating lips of the player. This interaction between the lip reed and the air tube is simplified by considering the lip reed as a mass spring system coupled to the tube resonator. As the airflow moves underneath the mass spring, the system is put into motion by the pressure forces arriving from the player's mouth, denoted by PM, and the pressure within the mouthpiece, denoted by P, which also includes the reflected pressure waves from the tube resonator. As the mass spring is moving up and down, it shapes the flow underneath it and varies the pressure within the reed channel and the mouthpiece. The mass spring starts vibrating considerably when the resonance frequency of the system is nearby one of the tube's natural frequencies. However, if we remove the tube from the system, the mass spring ceases to oscillate. In real life, though, the lips can still move and even vibrate from the interaction with the airflow generated by the mouth. Thus, we need to consider that self-oscillation of the system is possible and can be maintained by the airflow. This phenomenon is known as vortex-induced vibration, and an example of such an occurrence is the vibration of bridges or structures due to strong wind. Consider an object placed within a traveling flow. As the flow moves across the object, instabilities are formed in the layer around it. From these instabilities, alternating flow vortices on opposite sides are formed, which change the pressure distribution along the object's surface. This change in pressure distribution creates an alternating lift force, which puts the object into motion. The state-of-the-art approach in physically modeling the lip reed uses this mass spring presumption. Mathematically, the unknown variables within this interaction system are the displacement of the reed spring, the pressure within the mouthpiece channel, and the volume flow rate underneath the lip reed. These are derived from equations that describe the entire interaction, such as the forced harmonic oscillation of the mass spring and Bernoulli principle applied across the reed channel. From other previous works, the following mechanical details are also implemented in the model, including lip closing emulation, which is achieved by increasing the rigidity of the lip reed during collision, or the control of the resonant frequency of the mass spring through mass and elasticity adjustments. The innovative contribution to the model comes in the form of the Viv lift force added to the mass spring model. Consider the following mass spring object added within a traveling flow, and the following equation of a forced harmonic oscillation where the excitation force is the lift force, Lt. This lift force can be simplified as a velocity component to the harmonic oscillator, which varies the spring's damping coefficient. The lift force component is considered inversely proportional to the lip displacement. There is no exact formula to determine the proportions between the displacement and the lift force, so an empirical relation is derived, which would assure self-oscillation of the mass spring. A final detail is the addition of noise modulation for mouth-blowing pressure parameter PM. The pulse noise signal is used as a modulation function, which consists of a wide Gaussian noise passed through a bandpass and high-pass filter. The mean blowing pressure amount, PM0, is modulated based on the derived noise amount and the normalized lip displacement. The cutoff frequency of the high-pass filter is dependent on the reed aperture size. The presented model has been implemented as a real-time VST plugin, for which I will give now a short demonstration. Okay, now the VST plugin is loaded up. As we can see, the model can seem a bit intimidating with the sheer number of parameters available, but for interacting with the model itself, we only need to use 4 parameters, which are the lip resonant frequency, the tube resonant frequency, the blowing pressure amount, and the tube feedback, which is a feedback constant that controls the amount of reflected pressure that are being applied from the tube resonator towards the lip reed model. At this tube feedback value, the model is being affected both by the reflected pressure waves from the tube resonator and by the empirical lift force for the vortex-induced vibration. So now let's first start interacting with the model using only the lip resonant frequency. We increase the blowing pressure towards a high enough value, and then we can start interacting. So as we've heard, the sound of the model is pretty spot on. It's a pretty realistic sound of a brass instrument. Towards the higher frequencies, there are some noticeable artifacts, but all in all, it's of a good enough quality. It allows us to have a more continuous and expressive interaction with the model itself, possibly supporting a playing style like legato. Now, if we take this tube feedback and try to decrease it towards -1, we're basically increasing the amplitude of the reflected forces from the tube resonator, and we're subduing the influence of the lift force from the vortex-induced vibration. In this situation, we've observed that the model generates a much clearer sound, but the transience between the harmonics is almost non-existent and kind of limits the actual frequency range of playing for the system itself. Now, if we set the tube feedback to 0, we're basically removing the tube resonator from the lip reed model, and the model can vibrate by itself due to the lift force. Now, to achieve self-oscillation in this case, you need to strike a fine balance between the blowing pressure amount and the lip resonant frequency, because the model is pretty unstable in this situation. Okay, now we're gonna interact with the tube resonance frequency. In this case, we're basically controlling the length of the tube resonator. First, we're going to do some small changes to simulate the slide effect, and then we're going to do larger and larger changes. Finally, we're going to simulate the breath noise modulation capability. For this model, I've also implemented a MIDI mapping interface. The MIDI node frequency controls the lip resonant frequency and the tube resonant frequency. The MIDI modulation value and pitch bend control only the lip resonant frequency, while the tube resonance remains the same. The note velocity defines an initial amount of blowing pressure, and expression parameters like a MIDI expression pedal or the aftertouch feature of a MIDI keyboard can also add more blowing pressure to create a more natural envelope of the sound. Now, unfortunately, for this demonstration, I don't have a MIDI keyboard with an expression pedal or an aftertouch feature. Instead, I'm going to use an unassigned MIDI knob that can control the additional blowing pressure amount. As we have heard, the model is able to synthesize sound whose timbre is strongly similar to that of a general brass instrument. Another indication by how close we are to the real behavior of the model is through signal comparison. On the left side we have plots for the synthesized pressure signal. The figure A shows a pressure signal without noise modulation, and figure B shows with noise modulation. And on the right side we have, from a previous research, real-life measurements of pressure within the mouthpiece channel. The influence of VIV is remarkable, since it controls how audible the transients are between the harmonics of the tube, extending the available frequency range of playing. A shortcoming of the model is the difference between the lip resonant frequency set by the user, denoted by FL, and the measured fundamental frequency of the lip vibration, denoted by Fout, as we can see in this table of data. The difference is caused by the lip collision effects, which modify the rigidity of the mass spring, which in turn also changes the resonant frequency. Additionally, behavioral errors are also present in the model, which are due to the empirical design of the lift force and some other aspects of the implementation. An example of this would be the inaccurate dynamic behavior. As we increase in blowing pressure, PM, we would expect an increase in higher frequency harmonic energy, but this is not the case for this model. That being said, the developed VST plugin shows the potential of this embouchure prototype. The influence of additional aerodynamic forces show how the available frequency range is extended, which aids the expressive capability of the embouchure model. We've shown that the model supports more expressive playing styles like legatos and slides. The model can be improved certainly in many aspects. Two main topics of focus could be the redesign of the lip model to improve VIV interaction and a more realistic tube implementation. Thank you for watching. If there are any questions, I will be more than happy to answer them.
Hello, my name is Sylvan Willemsen, and today I'll be presenting for you our paper titled Real-Time Implementation of a Physical Model of the Tromba Marina. So first I'll go into what a Tromba Marina is, then I'll describe in detail the physical models that we use to simulate the instrument, and then I'll give some details on the implementation and end the presentation with a demo of the application. So first of all, what is a Tromba Marina? I'll show you a brief sound snippet so you can listen to it, actually. So as you can hear, it's kind of like this, it has a brassy timbre, or a timbre of a trumpet, but actually it is a bowstring instrument from the Middle Ages with a rattling bridge, or a shoe, due to its shape. So the string rests on this bridge and rattles it against the body as it is bowed, creating this brassy-like timbre, which is quite interesting. So the way that the instrument is played is by slightly damping the string at different locations using a finger or a knuckle, and these locations should be half the string, a third of the string, a fourth of the string, etc., to induce harmonics, and then it is bowed above the finger as opposed to what you would expect from a bowed string instrument such as a violin or a cello. So I'll quickly show you a video of me trying to play the Tromba Marina, which we had at the university, and trying to recreate the sound snippet that you just heard. So yeah, this is the way that it is played. So how did we go about simulating this? So we divided the entire Tromba Marina into three components. A string, which is a 1D system, the bridge we modeled as a 0D or point mass, and the body we modeled as a two-dimensional plate. So normally you use partial differential equations to describe motion of certain objects, and we describe them also in the paper in the form LQ equals 0, where L is a partial differential operator applied to a state Q, and this Q can be the state of the string, the bridge, or the body, and Q is defined over a domain X, which also depends on the system at hand. So for example, it will be one-dimensional in the case of the string and two-dimensional in the case of the body, for example, as we will see soon. And yeah, so let's go into the string. We have an operator now L subscript S for string, and a state U, which is defined over space chi and time t. And the operator looks like this, where this partial t and partial chi operators, they denote a derivative with respect to space, or time and space respectively. And then we have a list of parameters that describe the string, or the material of the string, where we have the material density, cross-sectional area of the string, etc., etc., etc. So this operator looks kind of scary, probably, for most of you. So let's just quickly go through what all these terms mean. So basically the acceleration of the string is dependent on a term that describes tension, a term that describes stiffness, and two terms that describe the damping as the string goes over time. Yeah, so that is the way that this operator is applied to the state U of the string. And then further on we will continue with this very brief notation of the form you can see in the top right, to have Ls of U, or applied to U, equals 0. Then we have the bridge modeled as a mass. So now we have a state variable W that is only dependent on time rather than being distributed in space. And the operator looks like this. So we have some tunable parameters, such as the mass of the bridge, the angular frequency of oscillation, and the damping. And again, we will use the shorthand notation to describe the movement of this string, or the mass. So now we have the body, where now we have a state Z that is described over two spatial dimensions, x and y, and over time t. And the operator looks like this, where now we have a derivative in two spatial dimensions, which is denoted by this delta, or 2D Laplacian operator. That's actually a second order derivative in two spatial dimensions. And then we again have some parameters by which we can tune the body. And then we end up with this shorthand notation again. So now we have three individual components: the string, the bridge, and the body, which are all equal to 0. So this means that individually they will work, but they are not interacting with each other. They are not connected. So we'll now go into the interactions between these components. So here you see a diagram of the bridge from the top, and our two main areas of interest are the bridge-body interaction and the string-bridge interaction. So we assumed that a horizontal movement of the string, the action it has on the bridge translates directly into a vertical movement at the body of the bridge, so that we can kind of stack all these components on top of each other rather than concerning this extra dimension. So let's look at the bridge-body interaction. So we modeled this as a collision, and the way we did this was to add a potential to the equations, where here our independent variable is eta, which basically describes the difference between the body at location xmp for mass plate and ymp, so the location where the bridge hits the body, and the bridge itself. So yeah, that difference is eta. And we have a operator, the subplus operator, which describes the positive part of. So you can see that if the bridge is below the body, eta will be positive, and there will be some potential that will create this collision effect. And then again, we have two tunable parameters, which are the collision stiffness and nonlinear collision coefficient, to tune this collision potential. So then we can add to the partial differential equations the derivative of this potential, which I'll refer to as the collision term. And so the mass now is equal to this potential here. And the plate has at the location xmp, ymp, which is denoted by this operator, which you can kind of see as a localizer. So it's a spatial direct delta function applied to this potential, to localize the effect of the bridge onto the body. And also note that here we have the potential which has a positive effect on the bridge, and here it has a negative effect on the body. So you can see that a positive and negative effect is applied to the bridge and the body respectively. So if we discretize this or implement this, we need iterative solvers. But the authors of this paper, Duchesky and Bilbao, in this context, propose to use a quadratic potential, so kind of rewriting this collision term a little differently, so that now we can add this to the partial differential equations, and now we can actually solve it explicitly. And I would like to refer you to their paper or the paper that I'm presenting now for more details on this. So moving on to the string-bridge interaction, rather than a collision, we model this as a connection. So the most important difference here is the use of absolute values rather than the subplus or one-sided operation, so that even if the difference between the mass and the string, in this case at string location chi sm, if that difference is negative, there will also be an effect, or there will also be a potential for collision. So in the same way, we can add this quadratic potential to both the string and the mass, and of course we need another spatial direct delta function to locate the bridge along the string, because we need a position for that. So to summarize, we started off with three individual components, which are the string, the bridge, and the plate. Then we took a look at the string bridge interaction, by which we added the potentials, now with their respective subscripts, SM for string mass. And this potential, or these collision terms, are dependent on the distance between the bridge and the mass, the bridge and the string at string location chi SM. Then we also added an other potential to the mass and a potential to the, or a collision term to the plate, where the distance between the bridge and the plate, eta mp, is influencing these collision terms, and the location on the plate, xmp, ymp, is what is taken into account here. Then the one thing that we're missing is the bow, so we actually need to interact with this system. And to do that, we can add an extra term to the string, which is this term. Again, we have a spatial direct delta function that localizes the bow on the string, and this is applied to a force and a nonlinear bowing function dependent on the relative velocity between the string and the bow. For more details, by the way, I would like to refer you to the paper. And lastly, we actually need a damping finger to induce the harmonics along the string. And we model this like this. Again, we need the spatial direct delta function, now at location chi of f. And so now we can actually play different pitches on the string. So for the real-time implementation, we discretize the entire system using finite difference time domain methods, but I won't go into details here, and I would like to refer you to the paper to show you how we did that. Then we use C++ and the JUICE framework to implement this in real time, and I think it's best if I show you a demo instead of talking about it. Alright, so this is the Sensor, and it is a device that contains about 20,000 pressure-sensitive sensors, with which it can detect X position, Y position, and Z position through pressure. So this is the application that we made. As you can see, we have here the string, the mass connected to the string or the bridge, and the body of the trauma marina. And here on the side we see the bridge and the body from the side. So we can interact with this setup by interacting with the sensor. So we can see that the bow moves as I move my finger. And the pressure is linked to bow force, and the vertical velocity is mapped to the bow velocity. And the second finger with which we interact with the sensor is mapped to a damping finger. So we can actually induce harmonics. And these lines that show up, they denote where the next harmonic should be. So as a guide to the player, where to place the finger to reach one of those harmonics. And interestingly, the higher up we go, the harder it is to play, just as with the real instrument, and the more pressure matters in order to actually get one of those harmonics. Both pressure in the finger and the bow. But yeah, so this is the application. We have 3 sliders here on the right, where we can change different volumes of the different components. So we can listen to the string only, like this. So we have the string, the body, and the string, the bridge, and the body as volume sliders here. So now we only listen to the string, so we lose the kind of rattling sound. We can also only listen to the bridge. Creates this, or we can only listen to the body. So only when there's a rattle, we can hear the body. Alright, so thank you very much for your attention. If you have any questions or are interested to know more, you can always send me an email through this address, and I hope you will have a nice virtual conference. Thanks.
Hello SMC 2020. This presentation is titled Insights into the String Barrier Interaction Dynamics based on high-speed camera measurements. My name is Dmitry Kartofelev. I'll be presenting this talk. In addition to me, this paper is co-authored by Juhan Arro and Professor Vesa Velimäki. We represent Tallinn University of Technology and Aalto University, respectively. In this talk, we'll present a time-stepping model for modeling collisions between a vibrating string and a rigid barrier, and compare this model against experimental measurements. This presentation is motivated by the fact that in guitar and other lutes, strings may collide against fretboards or other rigid objects, such as nuts, while played. The outline of this talk will be the following. Firstly, we'll present the string vibration and string barrier interaction models. Secondly, we'll explain the experimental measurement approach used in this paper. And finally, we compare the model outputs against the experimental data. So let's start with the string vibration modeling. The string is assumed to be ideal and lossy, given by the equation 1. Since the equation is linear, we can consider the wave equation shown here in the form 2 and add the losses separately. In our model, string vibration is obtained by directly exploiting the traveling wave solution, given here by expression 3, which states that the string shape is the superposition of traveling waves propagating in opposite directions. Here we have an example of the application of the traveling wave solution. As can be seen on the slide, we have selected a bell-shaped initial condition. Here the traveling wave moving to your right is shown with the green line, the traveling wave moving to the left is shown with the red line, and the resulting string shape is shown with the black thicker line. In order to add the string barrier interaction to the model, a purely kinematic approach based also on the traveling wave solution is used. Let's imagine a segment of a barrier shown here with the gray-colored region and the wave approaching it from the left. In order to guarantee that the string does not penetrate the barrier, a traveling wave moving to the right, meaning away from the barrier, is added and progressively modified in the manner showed on the slide. The above procedure can be written down as shown by expressions 4 and 5. Here x star denotes the spatial point where the string barrier contact is happening. Function b is the cross-section profile of the barrier segment shown above. At this point we stress that the function b can be selected arbitrarily. Let's take a look at a dynamic animation of the reflection discussed up to now. In order to simulate the waves approaching a barrier from both sides, same procedure is used. Waves approaching from the left will be reflected to the right and vice versa. In this simulation, we see a barrier with parabolic cross-section profile placed near the right edge of the string and a bell-shaped pulse interacting with it. If one is interested only in a single point's vibration time series, it can be easily extracted as shown in this animation, where a point position at the midpoint of the string is extracted. Now let's continue with the second part of the presentation. In order to experimentally measure the string vibration, we use high-speed video chymographic approach based on the line scan camera imagery. Line scan cameras use a single light-sensitive pixel array to produce a video frame. These frames are then combined into a two-dimensional image, called chymograph. The figure on the top shows the string placement with respect to the line scan camera's point of view, shown here with the red markings. Figure on the bottom shows a typical chymograph of a vibrating string. In order to extract the vibration waveforms from the recorded chymographs, we use a digital image processing, which is based on the 1D correlation of chymograph frames, which are usually referred to as the lines. The red line in the top figure shows the 500th line of the chymograph. Formula 6 is the correlation used. Here P is the image depth value of a line and K is the correlation kernel. The shape of the kernel K is usually selected to be a bell-like curve. String position will correspond to the maximum of the correlation product S, as shown by the formula 7. Figure on the bottom shows the calibrated vibration time series that corresponds to the chymograph above. At this point we can proceed to the final part of the presentation, where we compare the presented model with the experimental measurements. In order to test the proposed model, a monochord equipped with a rigid barrier with a circular cross-section profile was built. We used a guitar nylon string with string gauge 15 and length of 66 centimeters. We excited the string with a triangular initial condition. This initial condition and the placement of the barrier are shown on the top graph. The bottom graph shows the measured string waveform recorded at the spatial point x sub m. Let's start this simulation and see how well the proposed model does. On this slide we have another vibration simulation of the same setup, taking place at a later time, between 95 and 120 milliseconds. As we can see, the model predicts the waveforms relatively accurately, given its simplicity. In the frequency domain, our model does not do so well. Here we see the spectrogram of the simulated time series, and here the spectrogram of the experimentally obtained time series. A detailed analysis of the reasons for the differences in the spectrograms is given in the paper. The most important reason is the lack of stiffness and thus dispersive wave propagation in our model. Notably, the spectrogram shown on this slide features an initial pitch glide, which is missing from the modeled result. Analysis of the time and frequency domain results showed that string barrier collision dynamics features two distinct vibration regimes. The initial short-lasting, violent regime, characterized by the high-energy collisions with the resulting pitch glide, and the more peaceful regime characterized by a relatively stable frequency spectrum. In conclusion, we presented experimental measurement results of the string vibration against a rigid barrier. We presented a relatively simple time-stepping model for string barrier collision modeling. The model was able to predict the vibration waveforms in the time domain relatively well, given the nonlinearity of the problem, but the frequency domain results were not so good. We discovered that the string barrier dynamics features two distinct vibration regimes. And finally, the videochimographic experimental measurement technique used in this study was proven to be highly reliable for our purposes. The method is highly suitable for small object and small displacement measurements, especially if high spatial and temporal data resolution is required. This concludes this presentation. Thank you for your attention.
Okay. Okay, so hello everyone.
Hello.
Hey.
Hello.
Let's see if we are we online yet? No. Yep. I guess we are online now. So hello everyone. I'm Federico Vanzini.
Hello.
Very nice meeting you all virtually. I thank you all the presenters for their presentations. We've had, I think, a very nice session with a lot of interconnections between these papers, all dealing with nonlinear aspects of musical acoustics and physical modeling. And they're also linked by the fact that all of them are funded by the Nordic SMC network, which is providing a lot of contributions to SMC. We have a quite lively audience, so we have quite a bunch of questions. Let's start with Rares with the first presentation. So we had questions from Sofia Dahl, which says, thank you for a nice presentation. I realized that the mapping to an interface is not the part of the work, but still I would be interested if you have any thoughts on which of these parameters that would be most important. So can you
Yes.
tell us more about this?
Yes. Firstly, thank you for the question, Sophia. In regards to which of the parameter, I presume from the physical model, the most important parameter, I would say, is the pressure amount, because with the pressure you can control the envelope and the attack of the sound, and that's an important aspect of brass instruments. And as said briefly in the presentation, it's controlled by the initial velocity of the key and some additional amount like aftertouch or an expression pedal. That being said, in terms of MIDI mapping, it depends very much on the type of interface that we're using. So if you have like a very normal keyboard and just an expression pedal, it's gonna be a different type of interaction or variation as opposed to a Rolly keyboard that I've shown briefly in the presentation at the beginning. So yeah.
Okay, thank you. So we also have right now an additional question came in from Antonio Roda, which asks if the VST plugin is available. The VST plugin is available to try.
The VST, unfortunately, not, because the VST plugin, this project was done in collaboration with Audio Modeling, so the plugin is not open source per se. Yeah.
Okay, that's understandable.
Yeah.
Let's switch to Sylvain. We have quite a few questions for. So there were a couple of attendees, Chumur Erkut and Bolmel Metspatis, good, that's the nickname, who asked about generally, I would say, more details about the collision potential part of the model. I don't know if you can add something about that.
Yeah, so as I said in the presentation, it's based on a model by Duchesky and Bilbao of their 2019 DAFX paper. And it basically rewrites this potential in a different way so that we can discretize it explicitly. And basically the method that is used is a penalizing method. So what that means is that the two objects can actually penetrate, but once that happens, there's a strong opposing force, nonlinear opposing force to both of these objects colliding. So for more details on this quadratic potential, I'd like to refer you to their paper.
Right, perfect. Again, on the model, David Rocchesso was asking about the friction model, the stick slip model used for the bow.
Yeah, so we used a model that Stefan Bilbao proposed in his book, Numerical Sound Synthesis. And when I saw the question, I quickly made a drawing, so maybe you can see it's shaped like this. So it's an exponential function that is dependent on the relative velocity. So there. And yeah, so if the relative velocity is positive, then there's this curve that decides how much the force is then scaled. I actually don't know if this was mirrored in the Skype, but anyway. And a negative relative velocity would scale the force negatively. But if there's a very high relative velocity, you would only get a slip motion. So there's a very fine line for the bowing velocity in order to get sound. Yeah.
Perfect. So it's a classic memoryless model mapping velocity to force. Yeah.
Exactly. Yeah.
And one more question about the model is from Federico Fontana about the pickup points that you chose from the body to get the final output sound.
Yeah, so we kind of empirically did that. We have, as I mentioned in the demo, we have both, or the string, the mass, and the body that we can get sound from. And we kind of thought from the string you would have most sound closer to the ear, so higher up on the string. So I think we chose about like at 1/5 of the string. The details are in the paper. For that pickup point, and the body's pickup point, which is I think the most important part of his question, is directly where the bridge collides, because we think that also in the real instrument that is where the sound originates from that collision point. So we chose that as the output. And for the mass, it's of course just the state of the mass or the bridge. Yeah.
Okay, and finally one question from Andrea Valle, who's asking something, if you have anything more to say about the actual comparisons between the synthesized sounds and the real ones.
Right. We haven't done that yet. It would be very interesting to do some perceptual tests with recordings from the actual instrument and like the model itself. I think like a lot of work still needs to be done in parameter tuning, which is a pretty hard thing to do with these physical models and the amount of parameters that this model has. to make it sound as much like the real instrument as possible. But like informally, it was confirmed by us that that there were many similarities between the Tromba Marina that we had at the university and the model that we made. Yeah.
Okay. We also have a last-minute question by Roberto Bresin, who's asking zoom-out question. Why the Tromba Marina?
Well, physical models make it possible for instruments, rare instruments, or instruments that are just behind glass in museums, to be kind of resurrected again. So it would be interesting to find an instrument that almost no one knows and no one plays and almost doesn't exist, as opposed to a guitar, for example, or a violin, and try and model the interesting physics also in this case of the Tromba Marina. To make it available again to a wider audience. So that was kind of our goal, to resurrect this instrument, or at least towards the resurrection of this instrument. Yeah.
Right. Thank you very much. We have another question coming in, but maybe we should go back to the other papers and then go back to you if we have time.
Yeah.
I actually had one question for Dimitri. Very, very nice paper, and it's very interesting to see that as you said, such a simple, relatively simple kinematic model is able to account for such effect with such accuracy. I was wondering whether you can think at other features, additional features missing from the model, which could explain the discrepancies between the experimental data, the measured data, and the simulation from the model. One thing would be that I was thinking about is the collision itself. So you model the collisions as a completely inelastic phenomenon, where basically the displacement of the string is bounded to the surface of the obstacle of the. But I was wondering. I was wondering if you have considered other more sophisticated modeling approaches for the collision.
Well, yes, you could sort of introduce a force, a sort of an elastic force to it rather easily. So yeah, you could. So you're right. Yes, the modeling or the collision itself is the simplest way possible. It's not even physics; it's just kinematics, as you said. But yeah, you could define some sort of a potential that takes into account this amount that the string wants to penetrate, and just introduce a force that is proportional to that penetration, and that would be sort of an elastic collision. Did you hear me, or?
Yeah, absolutely. Thank
Okay.
you. Yeah. I also had a question for Raras. I was wondering if you could add anything more about the finite difference scheme that you're using for discretizing the model, and if you have thought about looking more into that, because I read in the paper that you're using quite a big oversampling factor to have to get stable simulations. That might be related to the fact that the difference scheme, finite difference scheme, is not optimal, or maybe in dealing with the nonlinear phenomenon involved in the simulations, and so on and so forth.
Well, for the finite scheme, the work for the finite scheme is mostly focused on simulating the mass spring movement, and while normally a finite scheme for a mass spring would be pretty basic to simulate, due to the fact that we can modify elasticity and modify the attenuation due to the vortex-induced vibration. This introduces some energy and can destabilize the model in certain aspects. Like, for example, if we are using a normal sample rate, not oversampled, if we are going towards a higher frequency, that can destabilize the model during the vibration. In terms of improvement on that, well, I think there needs to be more study on it.
I haven't gone too much into that aspect. For the last 6 months, I focused mainly on the simulating of the tube resonator, because in the paper we're using a more simplified model. But it's definitely a point of future work of improvement in the next future.
Right, thank you. So maybe we have time to take also the last question to Sylvine, which is by Marius Onofrey, who's asking whether you have control of choosing other pickup points in the VST, or maybe time varying pickup points.
That's interesting. I think for now we decided to have everything fixed, to be as close to the physical instrument as possible. But yeah, you're right. Like, physical models allow for like time varying anything. So it will be very interesting to kind of get like a pickup point that on the body goes around, or on the string that goes back and forth, for like a kind of flanging or vibrato effect. I should say, though, that the body has been modeled to be very damped. So once you get away from this collision point, you will have way less sound. But yeah, that is something that we could investigate. Definitely. Yeah. Thanks.
Okay, thank you. So I guess this concludes our question and answers session. I would like to thank again all the presenters for their presentations, and also the audience for their active participation. And I leave the mic to Andrea Valle.
Hello, hello all. Good morning, SMC community. I have just a short announcement. So now there is the piece by a very well-known composer, who is Alvin Carran. Sorry. The piece is Covidly Yours, Making Music with Anything. And after that, we present the piece Klingeln by Stefano Catena from 2019, that has not been broadcasted yesterday evening because of technical issues. Please note that this is a binaural piece, so wear your headphone. I'd like also to remind, on behalf of the music committees, that due to the COVID issue for this edition, we decided to stream the fixed media pieces that had been submitted for SMC. And as we have this opportunity of online participation, we thought it was important to let all the musicians in the C4 music submission category to participate, if they were willing to, of course, even if in this streaming format. So now music, and then we will be back with the next scientific session. Bye.
This is the new confusion.
Hi everyone, my name is Çağrı Erdem, and I will be presenting you our project in its paper on behalf of myself and my colleagues. Welcome and thanks for coming or virtually being here. Today I will tell you about how we tackle some challenges surrounding the concepts and methods of developing a virtual musical instrument for playing in the air. But first of all, what is it anyway? You can show your appreciation to a heavy metal band by headbanging and mimicking the guitar playing while listening at home or seeing the band live in a concert. That's what's called an air performance, right? I believe, on the other hand, that this term and all those air instrument championships also connotate some kind of mockery too, because isn't often thought that no physical instrument, no music making. But what about theremin then? For exactly 100 years now, you can make sound with it in the air. And nowadays, generating electromagnetic fields around antennas is just one way of playing in the air, considering that there are many options like motion capture and physiological sensing devices that allow the performer to use their body as part of the musical instrument. In this context, we can brief the previous work in two categories. On one end, there have been projects that aim to recreate the guitar virtually and often designed towards being commercially available products targeting a wider audience. On the other, there have been several different projects that actually use the body as part of the instrument and that were mainly created as artistic pieces. In this project, our aim is not to recreate the action sound couplings of electroacoustic guitar performance directly, but rather let them inspire the mappings in a new air instrument. In other words, we want to leverage the constraints and thus the sustainability of already acquired skills in playing a traditional instrument and reuse or repurpose it in making new sounds in interactive music, computer music contexts. To this end, one option among many is to use muscle sensing as the input in order to leverage the physical energy transfer during push and pulls experience while interacting with the instrument. So our overarching question is, how can we model relationships between action and sound in guitar playing using the muscle sensing as the input? So in this project, what we do briefly is to build a data set of bioelectric muscle signals and audio recordings of guitar players performing a set of basic sound producing actions, which are impulsive, sustained, and iterative. In order to build such a data set, we develop custom recording and processing software. Then we use this multimodal dataset to train a long short-term memory network that can predict the audio energy futures of free improvisations on the guitar, relying on a dataset of 3 distinct motion types. Okay, but before going any further into details, let me briefly mention here a few concepts and terminology that we will rely on. Music-related body motion is a continuous temporal phenomenon, whereas action can be described as the goal-oriented chunking of such continuous physical phenomena, what Godoy and Lehmann refer to as cognitive units. There are several types and categories of music-related body motion, but in this context, I will primarily focus on what is called as sound-producing actions, which are responsible for note production. Sound-producing actions then can be further divided into excitation actions, such as the right hand that excites the strings, and modification actions, such as the left hand modifying the pitch. The excitation can be further divided into 3 main categories according to the gestural sonorous objects model, which are impulsive, fast attack, continuous energy transfer, sustained, gradual onset, continuous energy transfer, and iterative, series of discontinuous energy transfer. An actual performance does not rely on these 3 conceptual categories, of course, but we can still think of an entire performance as comprised of different combinations of just these distinct sound-producing actions. What I mean is, consider, for instance, that you jump from one type of action to the other. Even though these would be completely different types of motion, as the goal points become temporally close, they merge into a newer co-articulated temporal shape, as you can see in the figure. So starting from there, as I just previously started, we can only rely on a dataset of such 3 fundamental action types, and then train a neural network to predict such co-articulated temporal shapes of an entire free improvisation. Okay, so to that aim, here is our research design. We conducted a series of experiments with 33 electric guitar players. In order to perform these experiments, we developed new tools for data acquisition, processing, and preparation, like further synchronization, interpolation, and so on. Using these recordings, we built a multimodal dataset of two kinds of EMG, one consumer grade, one medical grade, motion capture, video, and sound, consisting of the guitarist performing a set of basic sound producing actions in addition to free improvisation. We then performed statistical analysis using the mocap and medical grade EMG data, which is yet subject to another paper. For this project particularly, we relied on the recordings from the Maya armband, which are consumer grade EMG sensors, and the audio recordings to develop a preliminary machine learning model. In the experiments, all participants used the same performance setup, like the guitar, the amp, the plectrum, and so on. And each participant was recorded individually. The recorded part of the experiment relied on 4 tasks. Each was played separately with soft and strong dynamics and 2 improvisations. All given tasks focused on the notes B3 and C4 on the D string, played by index and middle finger. Each task was recorded as a fixed form track of duration 2 minutes and 16 seconds, along with a metronome click at 70 BPM, where participants were instructed to play for 4 bars, rest for 2 bars, and repeat the same pattern for 5 more times. Tasks were prompted through a custom Maxim SP patch on the screen, which allowed a more comfortable and efficient experiment process. And in the end, after excluding the broken data of 2 participants, we could build our dataset with a total of 310 tasks, including improvisations from 31 participants. Here you can see how those 3 distinct motion types reflect on the raw EMG signals and the resultant audio waveform plotted together. And here's a table that demonstrates the relationships between the bodily input and the sound output. Note that for now, we only focus on 2 of these, the raw EMG signals and the root mean square RMS feature of the resultant sound. Okay, so considering that one Maya armband has 8 EMG electrodes and that we use the EMG signals from both arms, a 16-dimensional array of raw EMG signals was fed into the neural network at every 50 samples, which is equivalent to 250 milliseconds considering the Maya armband's 200 Hz sampling rate. And then it was below the constraint of 300 millisecond acceptable delay that is suggested in the literature for myoelectric prosthetics. Here we used a relatively smaller array, which consisted of 5 hidden layers and 32 LSTM units in each layer. So what we do is we draw a 50 sample batch of training samples, use ReLU together with a hyperbolic tangent function in the output layer, calculate the training loss, where XRMS are the recorded values and X hat RMS are the values to be predicted, and N denotes the sliding window, which is 50, regarding the Maya armband sampling rate that I just mentioned. And finally, we use the Adam optimizer with a fairly small learning rate. So typically, at the first 5 epoch, the loss drop quickly and become stable after 10 epoch, which take around 3 hours. So overall, we could manage to finalize the entire training within the 12-hour limit of Google Colab. And in the results, as you can see, the model is generally capable of predicting the sound RMS. We were positively surprised to see that the model could predict the general trend of the sound energy in an entire free improvisation task, relying solely on these on the dataset of these single tasks. And this is how the model predicts the RMS of tasks actually played in the air. There is one problem though. Here you can see a kind of bass noise in the prediction, which shows a big influence of the raw EMG signal pattern, which we have to look into more in the future work. So to wrap up, here's a simplified diagram that demonstrates our workflow and the main environments we use. We first developed an updated version of our Python-based Maya to OSC bridge, which implements low latency support for multiple Maya armbands connected via individual Bluetooth low energy adapters. Then we developed another interface using PyAudio to record synchronized audio and sensor data. When it comes to processing, we first made the alignment and interpolation of our data, for which we mainly relied on SciPy. And then, while we used the raw EMG as the input, we extracted the RMS feature of the audio using Librosa library. And then we built our long short-term memory recurrent neural network model in PyTorch. Finally, we tested the model using the audio programming software SMC, where the sonification patch is built around a simple car+strong algorithm programmed in the GAN environment within Max, where the RMS value is mapped to the decay and damping parameters of the physical model. Briefly, this fairly simple synthesis method effectively shapes the white noise to simulate a guitar-like plucked string sound. We should also note that the onsets are extracted from the predicted values within the Python script and stored in the CSV file along with the RMS values and then sent into Max. So in the video, you can easily notice that when playing a series of fast attacks during the iterative task, onsets of the air instrument often lose the action sound synchrony. It's important because it reveals an important weakness of our strategy. As such, it motivated us towards modeling the entire spectrum of the recorded audio in the future work for better onset detection. So now let's see that demo video. Okay, so finally, the main contributions of this project are: we developed a custom software for interfacing the My armbands, recording and processing the data. Then we built a new multimodal dataset that will also be publicly available. Furthermore, all of these have also been and can further be used as a framework for motion sound analysis. And in the future work, we will work on improving the model by adding more features in the input and output, such as the IMU features from the sensor data and spectral features of the audio. We will then explore more that base noise that is biased towards the raw EMG signal pattern. We will develop a new framework that will run in real time and can be used to control a variety of sound synthesis methods. And what will ultimately follow is to conduct a thorough user study using this model-based control structure. Thank you for attention and being here.
Hi guys, my name is Yudong Zhao. Currently a third-year PhD student, studying in Center for Digital Music. Queen Mary, University of London. I'm very happy to be here to present my work to all of you. The title of my work is Identifying Master Violinists Using Note-Level Audio Features. The co-author is George Fazekas and Mark Sandler. The content of this paper is as follows. So, first of all, let's do the introduction of this paper. As we all know, the musical performance usually defined by three parts of people, including composers, performers, and listeners. The music structure, including pitch and rhythm, usually written by composers, and this expression is always given by performers, including their individual playing styles, their playing techniques, and their understanding of music. So the performances can be very different, while different performers play the same piece of music. In this paper, we focus on the performers' individual playing styles and the identification of the performers. So we'll listen to the same piece of music played by different performers, but their vibrato, their timing, and their energy is different. So let's listen to the first music piece. It's warm and peace, right? Let's hear the second one. The vibrato is more faster compared to the first one, so it gives us the different feeling. Let's listen to the second example. The second performer. It's different, right? So aim to the energy. The second one. So it's easy to find that different performer gives different feelings to audience. So let's see some previous performer identification methods. So first one is melody contour, or based on the frequency distribution. But the disadvantage of this work depends on the instrument itself. The second method is beat level, tempo, or beat level loudness. It also ignores the impact of the beat itself. The beat can vary from pieces to pieces. The third one is the proportion of vibrato in one music piece, but they ignore the detailed vibrato features. So the last is the energy contour. So the feature is quite simple and hard for multiple classification. The main contribution of this work is as follows. First one, we construct a novel dataset, then present a violinist identification method based on note-level vibrato feature. Also, we present another violinist identification method based on note-level onset feature. Finally, we identify master violinists using fusion features. Okay, let's see the methodology. We will present this part in these four aspects: dataset construction, two kinds of feature extractions, classification method, and result and evaluation. So this is a flow chart of this presentation. The dataset is from concerto recordings. Aim to the vibrato feature extraction method, we firstly do the solo vibrato note segmentation then do data pre-processing, then is the vibrato features extraction, then we go through a vibrato filter to get the feature distribution. For the onsets feature extraction method, the dataset is from concerto recordings, but the first pre-processing method is do the music piece segmentation, then is the selection of music piece, and then it's onset time annotation, and finally is onset feature calculation. After that, we get the feature distribution as well. After we get the feature distribution, then analyze the similarity, then get the performer identification result. So let's see the vibrato note dataset construction. First of all, we find 9 leading master players, including Heifetz, Auslacher, Parman, Zuckman, Menuhin, Stern, Accardo, Mutter, and Wengeloff. Then we find 5 violin concertos. All of them, they have played it before. So let's see how we annotate the vibrato note. So we just give a music piece. We just manually annotate the onset of offset of one solo vibrato note. Then we get the segmentation of the solo vibrato note from the original recordings. So let's see. This is the note segmentation. There's the second one, the third one, fourth one, and the fifth one. So from all the concertos, we annotate 162 vibrato notes from one performer's performance in total. So let's see the note onsets dataset construction. This is also the waveform of a very short of music piece. We just annotate the onset of each note like this. This table shows how many onsets annotations from each concertos. So let's see the second part is the data pre-processing. After we get the vibrato note segmentation, we need to do the extraction of fundamental frequency because all of the vibrato features are extracted from fundamental frequency. After that, we do the signal smooth via a zero phase filter. Let's see why we need to do that. So this is a vibrato note segmentation in waveform. Then, by using the P-in, we get the fundamental frequency estimation curve. To avoid the influence of the noise in the boundaries, we use a zero phase filter to smooth the signal. After the filter, let's see, the signal is much better. So let's see the filter extraction part. There are 4 kinds of vibrato features, including note level, average vibrato extent, note level average vibrato rate, and standard deviation of vibrato extent and vibrato rate. Let's see how we extract this. We list a vibrato extent feature extraction process in flowchart. As we introduced before, the F0 signal, just like this. Then we do the peak picking of this signal. Then we flip the signal over x-axis. We do the peak picking again. So we can easily get the every peak and trough in this signal, as the red dot shows. But there are still some fluctuations happened in the boundaries which are not caused by the vibrato. So according to the musicology paper and previous musicology series, we do the filter again to delete some points. So we get the every peak and trough caused by the vibrato in this case. So this is another part of the feature extraction. So in the onset feature, we extract only one feature named the note onset time deviation. In the top of this picture, it's a score of one music piece. Let's see also in the following bars in different color means the performance from different performers, from performer 1 to performer 9. First of all, we align the start time of this music piece to the 0 second. But from the second note, we can see the onset time is different from different performers. The dashed red line is the reference of each note onset time, which is calculated by the means of the onset time from every performer's onset time. So then we can calculate the note deviation. After we extract the audio features, we can calculate their distribution by using the 3 models, including histogram, kernel density estimation, and Gaussian mixture model. So this is the vibrato extent from the 2 performers, for example. So this blue histogram is from the high phase, and the pink one is from motor. Range of the vibrato using by high phase is more narrow than the motors. We use the feature distribution to describe the difference of different performers. Then we do the classification based on the single feature. As we mentioned before, there are 162 vibrato notes annotated from each performer's performance. We do the 8-fold leave one group out cross-validation. Aim to the data distribution, we calculate the KL divergence between each training set and test set. So aim to the fusion feature classification, which means we use different features together. We calculate the overall KL divergence by adding every single KL divergence value together and give them the same weight. So in this paper, the omega n is 1. So which means we give an equal weight for each feature's KL divergence result. Let's see the results. So we use AE to denote the average vibrato extent, AR denote average vibrato rate, and so on. First of all, let's compare the result based on different distribution models. So it's easy to find that the histogram performs good in the vibrato features, whereas in the onset time deviation feature, the KDE performs better. So then we do the comparison of the results based on different vibrato features. So this is the F-score result aimed to different vibrato features and the vibrato feature combination. We also can find that the VC performs best among all of them. So let's give a confusion matrix of the combined vibrato features classification result. So this is the timing deviation classification result, which is much better than using vibrato features. So there are 5 audio features in total, and we fuse them in different ways. So let's see how they perform. So we can find that the 3FF performs best. So let's see the confusion matrix. If we remember correctly, in the last confusion matrix by using the onset time deviation, the Menuhin and Oislacher confused with each other. But in this confusion matrix, we can distinguish them very clearly. Those F-measure result is not as good as using the onset time deviation only, but the discrimination for each performer is better than using that single feature. So let's see the conclusion. First of all, timing features works better than vibrato features. Second, although the timing feature performs the best F-measure result, the fusion features improves the discrimination for every performer. Third, Some feature works well for specific violinists, whereas the same feature is unhelpful for recognize other performers. Finally, the distribution methods don't strongly impact the classification result, but histogram works better for vibrato features, whereas KDE performs better for onsets feature. In the future, first of all, we will enlarge the size of vibrato dataset. Then we will combine different vibrato features using different weight, not just average. The third, extract more timing features and other kind of feature like timbre, dynamic, and so on. Finally, we will try other classification methods like decision trees or neural networks. This is a reference. Thank you very much.
Good evening everyone, I'm Luca Marinelli. I'm delighted to be here today to talk to you about our study on musical dynamics classification with convolutional neural networks and modulation spectra. Following a short introduction and discussion of relevant literature, we will move to discuss the main experiments performed with convolutional neural networks. Finally, a novel scalar descriptor based on modulation power spectra will be presented and tested against a baseline from a previous study. As many of you already know, musical dynamics indicate instrument intensity levels denoted in musical scores by marks usually ranging from pianissimo to fortissimo. Listeners have been reported to be able to recognize dynamics even when no reliable loudness information is available. This implies that variation in the timbre space of musical instruments are a byproduct of different dynamics. In a study by Vincier et al., which was performed on the same dataset used in this study, 3 descriptors of timbre were identified which were able to explain 72% of dynamics variance in scenarios without loudness information, namely attack slope, spectral skewness, and spectral flatness. The modulation power spectrum is obtained through a 2-dimensional Fourier transform of a spectrogram. In telecommunication, the term modulation refers to the process of multiplexing a signal that carries information, the carrier, with a signal that contains the message to be transmitted. Unfortunately, this definition implies specific constraints which do not apply to acoustic signals. So essentially, the modulation power spectrum of an acoustic signal is nothing but a mapping of the fluctuations of the signal that indicates how its energy changes over time and frequency. Anyway, this joint spectrotemporal representation was found to correlate with many timbre percepts, both in terms of sound identity and musical qualities. To explain the figure a little bit more into details, downsweeps in frequency are mapped to pixels in the right quadrant, whereas upward drifts in frequency appear in the left quadrant. Slower temporal changes are located near the zero of the axis, while faster changes result in higher temporal modulation towards the left and right of the image. Even if quite abstract, the MPS is appealing because it offers an invertible representation of the spectrum that is invariant to translations in the time-frequency domain. It is both psychoacoustically and physiologically motivated, as it correlates with timbre similarity ratings and it approximates the modulation transfer function of the auditory cortical networks. In addition, in 2 studies, it was successfully used for instrument recognition, as different instruments are mapped onto separated regions of the MPS. Let's now move to the main round of experiments from the present study. From an extensive dataset consisting of single notes of all instruments of the Beethovenian orchestra, which were played on their entire range and at 2 dynamics, from each sample, we extracted 1 second snippets, and where their starting points were the beginning of the sustained phase, as you can see in the corner, in the left corner. Then Equivalent rectangular bandwidth scaled and MEL scaled spectrograms were computed and normalized frame-wise by their respective RMS. Then, from the MEL spectrograms, we finally obtained the modulation power spectra. Finally, these three two-dimensional audio representations were then used to train the same convolutional neural network architecture. Given that no previous work on MTS or dynamics classification and CNNs was available, this architecture was selected through systematic trial and error. In the final proposed architecture, we have three two-dimensional convolutional layers with the first having 16 filters, a 7x7 kernel, and a stride of 3. So a strided convolution. The second and the third with 32 and 64 filters respectively, with a 3x3 kernel and a stride of 1. And finally, a softmax classifier that receives its inputs from a dense layer with 128 neurons. We found average pooling to reduce overfitting, and we used to regularize a classic dropout with dropout probability of 0.5. In order to test the robustness of the extracted features, the test sets in 3 experiments were partitioned in order to promote or avoid selection bias. From the first to the third experiment, we will see how selection bias is gradually increased and which consequences it has on the results of the models. In this first experiment, a 10-fold cross-validation was performed on the entire randomized dataset, and the differences in the results were tested for significance with the Wilcoxon test. We see how the MEL spectrograms perform slightly better than the other two audio representations. And also how essentially there is no significant difference in the performance of the models trained on ERB spectrograms and MPS. In the second experiment to increase selection bias, instruments from different timbre families are chosen to define 5 test sets. The instrument families are the following. We have clarinet for the single reeds, flute for the aerophones, oboe for the double reeds, trombone for brass, and violin for the bowed strings, or violin family. Here again, we see how time frequency representations score better results than modulation power spectrum. But clarification is due to for the flute test sets, because we have that all the aerophones contained in the dataset are solely present in the test sets, and this can help to explain why all models obtain suboptimal results on the flute test set. In the third and last experiment performed with convolutional neural networks, the 4 test sets consisted of all instruments from a specific timbre family. This means that similarly to the aerophones in the previous experiments, all samples in the dataset from each instrument family are contained in the respective test sets. In this case, we see how selection bias is strongly present, as the training sets are ensured to be non-representative of the test sets. And here, surprisingly, we see how the MPS outperform the 2 time frequency representation on all test sets. In a first attempt to throw some light on what we just saw, we thought to use saliency maps. The idea behind saliency maps is pretty simple. In a nutshell, the gradient of the output is computed with respect to the input image. This, in return, tells us how the output value changes with respect to small changes in the input. the average of the maps relative to all inputs for a specific class, so for all inputs for pianissimo and fortissimo, were computed for each family separately. As an example, here we can see the saliency maps computed on the pianissimo and fortissimo neurons, averaged over all single read samples. Saliency maps can be interpreted also as correlation maps, where a salient region basically represents an area of the input that highly correlates with the chosen target. By comparing the saliency maps of the pianissimo and fortissimo classes for each family, as we can see here, they are proposed in pairs. In the left, we have the pianissimo, and on the right, we have the fortissimo saliency maps. We can see that a clear pattern appears. For all families in the pianissimo maps, you can see a central salient region, which is also sometimes present on the fortissimo maps for all families. In order to further investigate to what extent this central area is alone effective in predicting the dynamics of single nodes, a scalar timbre descriptor is here defined as the average computed from 2 to 16 cycles per kilohertz of the sum of the temporal frames from 0 to 3 Hz of the MPS. We call this scalar descriptor steady spectral modulation. On the right, you can also see the distribution of the scalar descriptor on the entire dataset for the two classes. In the final experiment, we tested our novel descriptor against the spectral features selected in the NCR study for the same task and for the same dataset. But given that in our study we analyzed only the sustained phase of single nodes, the attack slope was left out from this comparison. This anyway should not raise too many concerns because the attack slope was found to be the least discriminative features, and as it could explain only 8% of the total variance. Here we see how on a 10-fold cross-validated linear discriminant analysis, the steady spectral modulation power was able to obtain a 44.8 error reduction. In conclusion, musical dynamics produce variations in the modulation space which are concentrated among low temporal modulations. What's more, the translation invariance afforded by modulation power spectra seems to produce features which are more robust against selection bias. In future studies, we propose to include different dynamics gradations between pianissimo and fortissimo, such as piano, mezzo piano forte, and mezzo forte, and then to try to train a regressor on the proposed scalar descriptor. In addition, this study showed that the translation invariance afforded by modulation power spectra enables the extraction of features that are more locally spaced in the input domain than those based on time frequency representation. This property of the MPS extracted features and the invertibility of the MPS, combined with visualization tools for neural networks, could facilitate the investigation of such features from a perceptual point of view. And that brings us to the end. Thank you so much for your interest and attention. And for those of you who have any question, I'll see you soon at the video call.
Hello, everybody. So glad we could all join each other together. So I am Becky Stewart, and I am coming to you from a heat wave in London. And so I hope you're all doing well where you are. And so I think we first all want to give a virtual round of applause to all three authors and their presentations. And we very much appreciated all of the excellent work we just heard from. So if you are just joining the session for the first time, the way this works is you will be putting in your questions into the YouTube chat. I will keep an eye out for those, and then I will pass those along to each of our authors for them to address and to answer. So I will try to keep an eye on that and do that. So let's go ahead and let's start with some questions in the order of the papers that we had them. So let's go back to our very first paper where we were looking at some air guitar performance, how it's mapped between a variety of signal inputs into a sound output. And let's start with the question that everyone always wants to know. Your data set and your models, will those be available for other people to access and to use?
Yes, definitely. Right now, the current version of the model is in GitHub, but now I'm working on kind of the improved version of the model, and I hope to release both the new version of the model and the data set by the end of summer. But I need to double check this ethical terms of when I can release the data set and everything. But hopefully soon. Yeah.
Excellent.
Yeah.
So people can kind of keep an eye on that. Maybe later you might want to, you could add your GitHub name to the chat or something like that if people want to just be able to follow you there.
Sure.
That could work. Excellent. So on to a little bit more of the meat of what you were working on. What was the balance of the input between the biometric signals that you were capturing from the Myo versus the video, that the mocap that you were using? And how, did you look at how each of those influenced the sound quality that was generated?
Well, first of all, I think I couldn't make it clear in the presentation, but in the model, we didn't use mocap or video at all. Like, it's only EMG signals that is used in the model. We use the rest of the data in a more analytical study, which is kind of subject to another paper, but no, they're not in the model. So that's one thing. And the second thing, I think I couldn't really understand the question of how it influences the sound quality. You mean the predicted futures, or is it the question?
That was my interpretation of the question. But
yeah,
I think it's pretty clear if the video wasn't even used in the model, well, then it didn't influence it at all.
No, but I have to say that the EMG signals, since we use the raw EMG signals, it influenced the predicted futures heavily. Actually, you can. I touched upon a little bit in the presentation, but imagine this idiosyncratic patterns of raw EMG or raw bioelectric signals, and you can see those patterns in the output. So this is, on one hand, this can be seen as the mistake or something wrong, but on the other hand, from a creative perspective, this can be even kind of a positive thing. So it's, it depends on how you want to use it, I think. So,
excellent. Yeah. Thank you. Then there was several questions kind of talking about the role of experts. So you had experts involved to create the data set. Did you have a chance to get any feedback from experts on the output model, or if there's future plans to have experts kind of perform using this model?
No, that's going to be in the second phase of the work, because unfortunately we couldn't really conduct a thorough user study after we built the model. But so the question, to address that question, we tested the model only with one expert air guitar player, which is myself, actually. But in the I would call myself as an expert air guitar player. But okay. So but in the second phase, like we want to do is to call most of those guitar players that took part in the first study, and then try out the system so that we can kind of compare their both in a quantitative and qualitative way.
Of course,
In the
great.
side.
And so, of course, you started with more kind of simplistic playing and kind of single notes because you got to start somewhere. Have you started to explore more complex, more musical playing and things like adding timbral effects from palm muting and these kinds of extra interactions?
Okay, so I think so there are multiple questions in this one question. Okay, first of all, we tested the model with the free improvisations from those guitars. So now the model is able to predict the RMS of an entire free improvisation from the guitars, but we couldn't really test it with air guitar performance because just using the RMS, you cannot really rely on the onset detection based on RMS. So when you're playing in the air, you cannot really have a good note onsets. So this is why we couldn't really test using some complex playing in the air. So that's one thing. And coming to the different playing techniques like palm muting. Well, first of all, I'm particularly interested in palm muting as an avid metal player, so a listener. And it's also a very interesting style because on just one limb, you can combine both excitation and modification action. Actually, you can excite the string and modify with your palm. It's a completely different. It requires a completely different data set, first of all. So if in the future, if anyone wants to collaborate to build that kind of data set, I would be super interested in investigate that. And lastly, about the timbral output, now in the second phase of the project, now I'm working on predicting the entire spectrum instead of just one single feature. So we will see how the input motion will contribute to the sound output. Right. Yeah.
Okay, excellent. Thank you so much. Well, I think we should, in the interest of time, move on to the second paper then. And so we move on to Yurong's paper about vibrato and violin performance. And you addressed this a little bit in the chat, but maybe just to be able to kind of readdress this to everybody who might have missed that. There was, again, the question around data sets and the releasing of the data.
Yeah, I think for dataset part, because copyright things, we cannot release an audio directly, but I think we can just release the annotation and maybe, for example, the onset and offset time in the specific audio, and also we can just release the version number of the CD recording. So if the maybe other users can just get the CD recordings as same as what I have used, so they can use annotation directly. So I think it's a kind of method to release that data set. Yeah.
Mm-hmm. Yes, things are always a little bit complicated, especially around copyright.
Yeah. Yeah. So
an answer we all are familiar with. Excellent.
Yeah,
just want to add a reminder if anyone wants to add any questions for Luca to answer as well, or any other questions that you think of while we're having these discussions, please just add them to the chat, and I'll keep an eye on that. It's not too late to contribute questions. But sorry, there was a question over the kind of the analysis, if there was analysis over kind of the evolution of the note as it was being played, and was the change in vibrato over time, was that being considered?
Yeah, so I think for that part is I think for the change of vibrato is also important by analyzing the individual playing styles of each performer. But the thing is also because the data set size, because it's hard for us to just label the like several hundred of notes from several concertos by labeling where the vibrato happens. But if we just define the system notes maybe for system 2 seconds or more, much longer notes, I think it's harder to annotate maybe 100 notes. I think is a little bit hard, but I think for the idea it's really good. I can try to build some model to just analyze the vibrato change, the individual vibrato change for each performer. So then I can maybe try to find some like characteristics for each performer, and maybe there will be some discoveries or not, but I'm not sure. Yeah.
Yeah. And then there was some interest if you could talk a little bit more about the timing features that you did use, and for example, kind of what normalization was used to work with these and so on.
Yeah, I should say sorry for I just ignored the part of the normalization in the presentation. Yes, exactly. I did the normalization things after I extract the timing onset deviations. Then I just use maybe 0 to 1 normalization for each performer's onset deviation result. So after that, I just build the different models to get the distribution of the timing onset features. So then just did the similarity analysis and also do the identification things. Yeah.
That's great. Thank you so much.
Thank you so much. Thank you.
Great. So let's move on then. We have a couple more minutes still doing good on time, and move on to Luca and your paper. Thank you so much.
Thank you.
Let's just round out with the same question to you as well. For dataset access and kind of open data, are there any plans in being able to release this dataset that you've been working on and the annotations that went with it?
The dataset is already open access. You can access it through the link provided in the paper, is in the deposit ones of the TU Berlin. And the annotation to everything is already there. The code, on the other hand, I have to be honest here. This was my master thesis project, so I have been doing it really not professionally. Now I have been working as a developer, so I really have to clean it up before releasing it.
Yes.
But
yes,
yeah,
no.
anyone who is interested, just email me. There is the email on the paper, or I will soon move to London at the C4DM, so maybe also there you will be able to reach me. And yeah, who is interested, I will forward it to their email. No problem.
Excellent. That's great to hear. It's great to hear open data being shared for other researchers to be able to build off of as well. And yes, I think everyone feels self-conscious about their own code that they write for their research, certainly. I have a question, but let me make sure no one else had a question that I'm stepping over first. No, great. So you've looked at quite the extremes in the dynamic range of the individual instruments. What do you think putting in a more kind of mezzo kind of dynamic, somewhat more of a middle point or even multiple middle points between the very quiet and the very loud, do you think that would significantly change the work and the outcomes? Do you think it would be kind of a kind of linear space between the two, or do you expect that there'd be far more complicated things to introduce this extra kind of point of loudness?
Regarding which kind of kernel to use in the regressor, well, it has to be still to be decided. We don't have the data yet, but I would imagine, given that we have this scalar descriptor that showed a really strong separation. Also, intra-instrument, I showed in the presentation only the distribution on the entire data set, but data was also the distribution was also analyzed per each instrument family. And I think it was really strong and really clear between pianissimo and fortissimo. So I would imagine some kind of regressor could be totally built on that. Maybe linear, who knows, yes.
Sometimes such simple things are elegantly appropriate, and sometimes the world's not so simple. Excellent. Well, thank you so much. I'll do one more glance at the chat to make sure there's no other last minute questions. I don't, which means we are perfectly within time, which is fantastic. And so we have the next session will be a poster session that will be starting shortly. But I once again thank all of the authors for their contributions or for their presentations. And we're sorry that we can't all be together, but very glad that we will still be able to learn from your work and have you share it with us. So thank you.
Thank you.
Thank you.
Thank you very much.
With the supercollider extension class FB1, a feedback feed-forward relation can be written in a form which is close to usual DSP notation and independent from the current block size. Using arbitrary nonlinear operations in the feedback chain gives many possibilities for experimental synthesis. The basic example in the left column shows how a simple one-pole filter could be written. The definition goes into the function in the third line with two arguments named in and out. Then the index 0, written in square brackets, denotes the current, and index 1 the previous input or output sample. Main options are an arbitrary and variable loopback depth and array-valued feedback feed-forward, which allows the definition of complicated cross-feedback relations. Besides the easy definition of linear and nonlinear filters, which are not contained in SuperCollider, the use of arbitrary arithmetic or trigonometric operators can lead to interesting results as well, as the implementation of conditions into the defining function. FP1 is also used as a base for FP1 ODE, a class for the codification of ordinary differential equations. The implementation of FP1, following a concept of Nathaniel Virgo, iteratively applies the defining function to control rate Eugenes while building the synth-def graph. This can result in a high number of Eugenes, but not necessarily a high CPU load. It's a good idea to take a lower block size while interactive work in order to reduce compile times. Please see further credits and links to software in the right column. Thanks for your attention.
Hello. As we can see in this SMC conference, physics-based modeling is not a vivid research topic. But at the same time, composers, musicians, artists still hardly jump into the design of their authored physical models. One of the reasons may be that researchers and software designers still need to invent tools that serve better, in depth, the very difficult task of designing a physical model in daily creative practices. Our paper introduces the Physics Networks Scripting Language, PNSL, which enables scripting the design of physical models for sound and music computing, of course, but also visual animation and VR, gesture interaction with haptics, and others. On the side of the core physics-based system, PNSL roots on masses interactions networks, as defined in the good old Cordis-Anima formalism. On the side of the programming languages, it builds over the tool command language Tcl. Then, PNSL enables designing your own physics-based models, possibly complex, with hundreds of thousands or millions elementary masses and interactions, and with any topology, included carefully crafted parts like a delicate lace if you want. During the poster session, I hope we can go through the specificities of this creative programming system, share examples, and more important, discuss with all of you. So, thank you very much. Bye-bye.
Hi, my name is Giacomo Lepri, and I am based in Queen Mary University of London. My paper introduces a set of reflections comparing the research domain of translation studies and data sonification. This to provide new conceptual metaphors for the understanding of sonification and related fields. Considering the similarities between translation and sonification might indeed provide a set of versatile and inclusive tools to frame different sonification approaches and purposes, including scientific investigations, design research, and art production. This research is grounded on the idea that both sonification and translation share a common element. They are concerned with the transfer of information from a semantic system to another. Sonification is then framed as an act of interpretation, where the designer aims to adapt digital information into acoustic signal. According to this mindset, sonification can be conceived as a process of negotiation, where data are translated into sound, taking into account the cultural framework of the target community. This novel framing might help to open design spaces and differently approach sonification tasks based on their context and purposes.
Hello, I'm Ramon Romeo, and I'm gonna present this poster. It's Rhythm Rangers, an evaluation of beat synchronization skills and musical confidence through multiplayer gamification influence. The aim of this work was to evaluate participants' beat synchronization skills through rhythm training with a multiplayer game. In order to achieve this, a baseline skill evaluation test was constructed before and after a 4-player rhythm game. For the baseline test, players needed to synchronize their claps to a metronome and a simple beat audio loop, while for the game, players needed to synchronize to 4 different audio loops and follow some specific game rules we designed. For this purpose, we designed and implemented our own devices and ecosystem for the game. 4 wearable devices were attached to the back of the player hands and detected their claps. As you can see, the device in the bottom left corner on the poster. And also we had another device that served as a visual metronome and decided the game rules. The results obtained from the experiment show that players improved their average local scores for the simple beat audio, but not for the metronome loop, and a dependent sample t-test corroborated this, showing that the game had significant effect on the improvement of the results for the simple loop. But most important also, all players claim to have had fun playing the game.
This study looked at how the use of the Chameleon melodic harmonization assistant may have influenced the creative process of harmonizing a melody. To this end, our participants harmonized 2 very similar melodies, the first on their own, while the second after having interacted with Chameleon. Well, to give you an example, this is probably the most typical and therefore the most expected harmonization of the second melody. Let's have a listen. Now, when a participant comes up with something like this instead, the question that arises is whether the differences between the most expected harmonization and what was produced by the participant eventually can be attributed to an influence of the use of Chameleon. I'll be very glad to discuss these findings in the poster session.
In this contribution, we discussed the multifaceted aspects of designing and implementing real-time physically based virtual musical instruments. This involves a balancing act between model design, efficient implementation, expressive control, and accessibility. We illustrate these aspects through 3 recently developed virtual musical instruments using mass interaction modeling: a virtual harp, a bowed mesh, and a bowed string model. We present a new element for mass interaction modeling called proxy module. It allows to smoothly interpolate topological connection points on regularly disposed matter, such as discrete strings or meshes. This enables changing the location of coupling points between structures inside a model, such as excitation points or contact points, giving a much larger expressive palette to design models. Regarding real-time performance, we offer a benchmark of various mass interaction implementations in C++, comparing them in some cases to finite difference schemes. In cases where efficiency is crucial, we may also benefit from manual AVX vectorization, which speeds things up. Two of these instruments have been integrated into artistic works, posing new challenges in terms of flexibility and adaptability in regards to compositional needs. For more information regarding our work and mass interaction modeling, head over to micreative.eu.
In this paper, we present an endless knob controller which can provide several resistive force feedback, and in particular we figured to apply such technology to multimedia productions. In multimedia production, many activities consist of repetition of several iterations, each consisting of a repetitive task. In such scenario, a multimodal feedback can reduce the cognitive load associated with the repetitive task, like parameter selection or waveform browsing. In particular, the tactile feedback can reinforce visual information to facilitate the detection of specific features of the waveform. Our knob generates the illusion of active feedback thanks to a programmable electromagnetic braking system driven by an Arduino microcontroller. The knob can be programmed to render different effects by modulating the braking force. Examples are dead ends, barriers, fixed or variable torque. In the video on the right, you can see a simple demo showing different effects applied to a waveform. In particular, it's possible to feel the instantaneous amplitude of the waveform, to explore the waveform within a fixed time window, or to modify some effect parameter. For each parameter, the resistance changes consistently with the visual tick display. For further information, please read the full paper or contact us.
Hello, my name is Karolina Pravda, and I am a doctoral candidate at the Acoustics Lab of the Aalto University in Espoo, Finland. Today I would like to invite you to get acquainted with the study I did together with Vesa Välimäki and Stefania Serafin, the evaluation of accurate artificial reverberation algorithm. In the study, we checked how well does the feedback delay network algorithm with cascaded graphic equalizer as an attenuation filter reproduce room impulse responses. In the objective evaluation, we compared the measured impulse responses with the ones modeled using the proposed algorithm. The comparison shows that the decay in the mid-frequencies is reproduced well, while there is an overshoot in energy of the high frequencies. We also performed a subjective evaluation in the form of a listening test, in which we asked participants to assess the differences between measured and modeled reverbs, according to the 4 qualities of sound. The results show that most of the time, slight or no differences were reported. If you want to know more about the research and the results, I invite you to read the paper, which is included in the conference proceedings. If you have any questions, please do not hesitate to contact me.
Welcome everyone, I'm Matteo Amadio and the project I'm presenting is a work in progress that started in 2019 as my thesis for the bachelor course in electronic music at the Conservatorio of Music Cesare Pollini of Padua. Alberto Novello, which is co-author of this paper, was the thesis supervisor. In this research, we present a set of real-time modules that digitally enhance the performance of a drummer. These modules extract rhythmic information from the multi-channel audio acquired using simple microphones onto the different drum parts. Based on the predicted tempo, the software generates complex patterns that can be manually controlled through high-level parameters or can be left automatic to adapt to the drummer's specific style. Our main goal is to sample the acoustic sound of the drums with all its nuances and extract high-level features such as tempo, cue onsets, and density. Then we rhythmically enrich the performance by counterbalancing the drummer's style with electronic sounds generated by some audio processes that are applied on the sound of the drum kit. Such an interactive system is intended mainly for an improvised solo performance that confronts a human drummer with a computer, but it could also be effectively employed in improvisations with larger ensembles or interactive installations. By scanning the QR code on the poster, you can find a video example that shows the functioning of the system when used for an improvised solo performance.
The major downside of additive synthesis techniques is the amount of time-varying parameters required for their control. Our work proposes a method to exert a high-level control over additive synthesis attributes and their evolution over time. This approach allows to master a large amount of synthesis parameters through the definition of the behavior of a system, of which the parametric control is an emergent property. EET systems are network systems specifically designed to control the amplitude of additive synthesis partials. Such systems can be described as weighted direct graphs, in which the nodes are capable of migrating the quantity they contain, referred to as energy in this context, to other nodes through the arcs connecting them. The scheme of connections and the weights of the arcs are conveniently described as adjacency matrices, which define the overall behavior of ET systems. Given an initial state and computing the energy transfers against time, we can attend the spontaneous evolution of the system. It is crucial to bound its behavior between arbitrary limits in order to use it as a control device. The bounding is mainly accomplished in 3 ways. Clipping functions define the maximum and minimum values each node can take. A damping parameter is provided in order to arbitrarily interfere with the spontaneous evolution of the system. And last, a value called target amplitude provides a constant correction of the total amount of energy contained in the system. The music track you are currently listening to is a musical study created using additive synthesis processes controlled by ET systems only. Thank you for your attention.
With the supercollider extension class FB1, a feedback feed-forward relation can be written in a form which is close to usual DSP notation and independent from the current block size. Using arbitrary nonlinear operations in the feedback chain gives many possibilities for experimental synthesis. The basic example in the left column shows how a simple one-pole filter could be written. The definition goes into the function in the third line with two arguments named in and out. Then the index 0, written in square brackets, denotes the current, and index 1 the previous input or output sample. Main options are an arbitrary and variable loopback depth and array-valued feedback feed-forward, which allows the definition of complicated cross-feedback relations. Besides the easy definition of linear and nonlinear filters, which are not contained in SuperCollider, the use of arbitrary arithmetic or trigonometric operators can lead to interesting results as well, as the implementation of conditions into the defining function. FB1 is also used as a base for FB1 ODE, a class for the codification of ordinary differential equations. The implementation of FB1, following a concept of Nathaniel Virgo, iteratively applies the defining function to control rate Eugenes while building the synth-def graph. This can result in a high number of Eugenes, but not necessarily a high CPU load. It's a good idea to take a lower block size while interactive work in order to reduce compile times. Please see further credits and links to software in the right column. Thanks for your attention.
Hello. As we can see in this SMC conference, physics-based modeling is not a vivid research topic. But at the same time, composers, musicians, artists still hardly jump into the design of their authored physical models. One of the reasons may be that researchers and software designers still need to invent tools that serve better, in depth, the very difficult task of designing a physical model in daily creative practices. Our paper introduces the Physics Networks Scripting Language, PNSL, which enables scripting the design of physical models for sound and music computing, of course, but also visual animation and VR, gesture interaction with haptics, and others. On the side of the core physics-based system, PNSL roots on masses interactions networks, as defined in the good old Cordisanima formalism. On the side of the programming languages, it builds over the tool command language Tcl. Then, PNSL enables designing your own physics-based models, possibly complex, with hundreds of thousands or millions elementary masses and interactions, and with any topology, included carefully crafted parts like a delicate lace if you want. During the poster session, I hope we can go through the specificities of this creative programming system, share examples, and more important, discuss with all of you. So, thank you very much. Bye-bye.
Hi, my name is Giacomo Lepri, and I am based in Queen Mary University of London. My paper introduces a set of reflections comparing the research domain of translation studies and data sonification. This to provide new conceptual metaphors for the understanding of sonification and related fields. Considering the similarities between translation and sonification might indeed provide a set of versatile and inclusive tools to frame different sonification approaches and purposes, including scientific investigations, design research, and art production. This research is grounded on the idea that both sonification and translation share a common element. They are concerned with the transfer of information from a semantic system to another. Sonification is then framed as an act of interpretation, where the designer aims to adapt digital information into acoustic signal. According to this mindset, sonification can be conceived as a process of negotiation, where data are translated into sound, taking into account the cultural framework of the target community. This novel framing might help to open design spaces and differently approach sonification tasks based on their context and purposes.
Hello, I'm Ramon Romeu, and I'm gonna present this poster. It's Rhythm Rangers, an evaluation of beat synchronization skills and musical confidence through multiplayer gamification influence. The aim of this work was to evaluate participants' beat synchronization skills through rhythm training with a multiplayer game. In order to achieve this, a baseline skill evaluation test was constructed before and after a 4-player rhythm game. For the baseline test, players needed to synchronize their claps to a metronome and a simple beat audio loop, while for the game, players needed to synchronize to 4 different audio loops and follow some specific game rules we designed. For this purpose, we designed and implemented our own devices and ecosystem for the game. 4 wearable devices were attached to the back of the player hands and detected their claps. As you can see, the device in the bottom left corner of the poster. And also we had another device that served as a visual metronome and decided the game rules. The results obtained from the experiment show that players improved their average local scores for the simple beat audio, but not for the metronome loop, and a dependent sample t-test corroborated this, showing that the game had significant effect on the improvement of the results for the simple loop. But most important also, all players claim to have had fun playing the game.
This study looked at how the use of the Chameleon melodic harmonization assistant may have influenced the creative process of harmonizing a melody. To this end, our participants harmonized 2 very similar melodies, the first on their own, while the second after having interacted with Chameleon. Well, to give you an example, this is probably the most typical and therefore the most expected harmonization of the second melody. Let's have a listen. Now, when a participant comes up with something like this instead, the question that arises is whether the differences between the most expected harmonization and what was produced by the participant eventually can be attributed to an influence of the use of Chameleon. I'll be very glad to discuss these findings in the poster session.
In this contribution, we discussed the multifaceted aspects of designing and implementing real-time physically based virtual musical instruments. This involves a balancing act between model design, efficient implementation, expressive control, and accessibility. We illustrate these aspects through 3 recently developed virtual musical instruments using mass interaction modeling: a virtual harp, a bowed mesh, and a bowed string model. We present a new element for mass interaction modeling called proxy module. It allows to smoothly interpolate topological connection points on regularly disposed matter such as discrete strings or meshes. This enables changing the location of coupling points between structures inside a model such as excitation points or contact points, giving a much larger expressive palette to design models. Regarding real-time performance, we offer a benchmark of various mass interaction implementations in C++, comparing them in some cases to finite difference schemes. In cases where efficiency is crucial, we may also benefit from manual AVX vectorization, which speeds things up. Two of these instruments have been integrated into artistic works, posing new challenges in terms of flexibility and adaptability in regards to compositional needs. For more information regarding our work and mass interaction modeling, head over to micreative.eu.
In this paper, we present an Anderson knob controller which can provide several resistive force feedback, and in particular we figure to apply such technology to multimedia productions. In multimedia production, many activities consist of the repetition of several iterations, each consisting of a repetitive task. In such scenario, a multimodal feedback can reduce the cognitive load associated with the repetitive task, like parameter selection or waveform browsing. In particular, the tactile feedback can reinforce visual information to facilitate the detection of specific features of the waveform. Our knob generates the illusion of active feedback thanks to a programmable electromagnetic braking system driven by an Arduino microcontroller. The knob can be programmed to render different effects by modulating the braking force. Examples are dead ends, barriers, fixed or variable torque. In the video on the right, you can see a simple demo showing different effects applied to a waveform. In particular, it's possible to feel the instantaneous amplitude of the waveform, to explore the waveform within a fixed time window, or to modify some effect parameter. For each parameter, the resistance changes consistently with the visual tick display. For further information, please read the full paper or contact us.
Hello, my name is Karolina Pravda, and I am a doctoral candidate at the Acoustics Lab of the Aalto University in Espoo, Finland. Today I would like to invite you to get acquainted with the study I did together with Vesa Välimäki and Stefania Serafin, the evaluation of accurate artificial reverberation algorithm. In the study, we checked how well does the feedback delay network algorithm with cascaded graphic equalizer as an attenuation filter reproduce room impulse responses. In the objective evaluation, we compared the measured impulse responses with the ones modeled using the proposed algorithm. The comparison shows that the decay in the mid-frequencies is reproduced well, while there is an overshoot in energy of the high frequencies. We also performed a subjective evaluation in the form of a listening test, in which we asked participants to assess the differences between measured and modeled reverbs, according to the 4 qualities of sound. The results show that most of the time, slight or no differences were reported. If you want to know more about the research and the results, I invite you to read the paper, which is included in the conference proceedings. If you have any questions, please do not hesitate to contact me.
Welcome everyone, I'm Matteo Amadio and the project I'm presenting is a work in progress that started in 2019 as my thesis for the bachelor course in electronic music at the Conservatorio of Music Cesare Pollini of Padua. Alberto Novello, which is co-author of this paper, was the thesis supervisor. In this research, we present a set of real-time modules that digitally enhance the performance of a drummer. These modules extract rhythmic information from the multi-channel audio acquired using simple microphones onto the different drum parts. Based on the predicted tempo, the software generates complex patterns that can be manually controlled through high-level parameters or can be left automatic to adapt to the drummer's specific style. Our main goal is to sample the acoustic sound of the drums with all its nuances and extract high-level features such as tempo, cue onsets, and density. Then we rhythmically enrich the performance by counterbalancing the drummer style with electronic sounds generated by some audio processes that are applied on the sound of the drum kit. Such an interactive system is intended mainly for an improvised solo performance that confronts a human drummer with a computer, but it could also be effectively employed in improvisations with larger ensembles or interactive installations. By scanning the QR code on the poster, you can find a video example that shows the functioning of the system when used for an improvised solo performance.
The major downside of additive synthesis techniques is the amount of time-varying parameters required for their control. Our work proposes a method to exert a high-level control over additive synthesis attributes and their evolution over time. This approach allows to master a large amount of synthesis parameters through the definition of the behavior of a system, of which the parametric control is an emergent property. EET systems are network systems specifically designed to control the amplitude of additive synthesis partials. Such systems can be described as weighted direct graphs, in which the nodes are capable of migrating the quantity they contain, referred to as energy in this context, to other nodes through the arcs connecting them. The scheme of connections and the weights of the arcs are conveniently described as adjacency matrices, which define the overall behavior of ET systems. Given an initial state and computing the energy transfers against time, we can attend the spontaneous evolution of the system. It is crucial to bound its behavior between arbitrary limits in order to use it as a control device. The bounding is mainly accomplished in 3 ways. Clipping functions define the maximum and minimum values each node can take. A damping parameter is provided in order to arbitrarily interfere with the spontaneous evolution of the system. And last, a value called target amplitude provides a constant correction of the total amount of energy contained in the system. The music track you are currently listening to is a musical study created using additive synthesis processes controlled by ET systems only. Thank you for your attention.
Hello, my name is Yoros Marendakis and I'm from Oxford University College in Norway. I'm going to present Pictorize, which is about the development and evaluation of an algorithm for transforming image region luminosity to sound brightness for monitoring location. Here's a little overview of my talk, which contains an introduction, background, a presentation of the algorithm, evaluation, discussion, and conclusions. The motivation behind this work is to create auditory location monitoring. That is, an algorithm that allows users to monitor the location of objects based on sound. Location monitoring systems are typically visual and can require significant visual attention resources. This can be unnecessary, especially for slow-moving or unpredictable targets. Therefore, in these such cases, auditory location monitoring could reduce demands of visual attention and even lead to dual-task performance improvements. However, a typical finding is that there is a cost on task accuracy when people perform auditory monitoring. And this is because the monitoring of values of task-relevant parameters may not be possible to perform with the same precision using audition compared to vision. Nevertheless, the objective of the study is to develop an algorithm that creates a causal mapping between the location of objects and the sound that the algorithm generates. We want to work with video input from moving images, as most monitoring systems already provide this, and therefore our algorithm could be used in such systems to create multimodal systems or audio-only systems, for example. Finally, we want to evaluate how well this algorithm can be used for tracking location. Let's go on with the background. To get some inspiration about how to develop our algorithm, we looked into image sonification techniques. There we have three major categories. The first is spectrogram mappings, the second object-based mappings, and the third direct mappings. Spectrogram mappings work by mapping pixel intensity, but also pixel location, along the image X and Y axis to spectrogram beam attributes, such as amplitude, frequency, time, or spatial location. The output is sonified using the inverse or time Fourier transform in most cases. Object-based mappings do not operate directly on image pixels, but rather they use machine learning to track objects on the image and then use a certain mapping to inform users about object properties and location. For example, typically they use a distinctive timbre for its objects, which is presented from a spatial location that corresponds to the location of the object on the image. The third category, direct mappings, is not really a mapping because they aim to create an auditory perception that directly conveys elements of a visual scene. A common approach, for example, in this category is to present clicks at an intensity and location that maps directly to the intensity of individual pixels or pixel groups from a visual scene. Interestingly, these mappings do not involve a translation or mapping process. Looking into evaluation results in the literature, it's easy to find out that the spectrogram technique, even though it's relatively widely used, is relatively hard to apply for our purpose, because users need to be trained extensively before they can recognize the contents of a visual scene based on the output, or the sound output of the algorithm, and may face difficulties when the new scripts are presented to them. Object-based techniques work relatively well as long as users can learn the mappings that are involved, but they face difficulties again in complex scenes, and they rely heavily on sound specialization and machine learning, and therefore they become problematic when these approaches fail or become unstable. Direct mappings are more interesting because they rely on a perceptual process, and therefore they may be more robust and generalizable. The rasterization approach, in which we refer to in the paper, is particularly relevant to this work. This approach basically reads pixels from image regions into a vector, which is then played back to users using scan synthesis. Unfortunately, the mapping that is created is not causal because of the synthesis technique. Therefore, it's not exactly possible to use this technique for location monitoring. To summarize, our research questions remain: so how can we encode to the object location into sound timbre? And assuming that we develop this algorithm, how well this can be used to differentiate between locations. So let's go on and present the algorithm that was developed here. And the algorithm extends the direct mapping techniques, and in particular the rasterization approach. It works by separating an image into regions. In this case, these are 12 regions, so you can imagine a grid with 12 subdivisions that is applied directly on a video like this, like the one you have here. Then for each image region, a number of operations are performed. The first two are transformation to grayscale and background subtraction. The next step is basically what differentiates this algorithm from the state of the art, and in particular the fact that we calculate a histogram of pixel intensity values, which is smoothed using a low-pass filter and then mapped to a sound spectrum. One such spectrum is generated for each image frame and image region, which is then transformed in the time domain using the inverse short time Fourier transform. And then the sound signals from all the regions are superimposed to create a single channel sound output. Notice that because of the background subtraction, regions in which no object is moving do not produce a sound output. So here is an example of applying the algorithm to one of the videos that we used in the experiment we present next. In this video that you see here, you see that there is a little car that is moving on the screen. When we apply the algorithm, it's easy to imagine that because of the background subtraction, sound is only generated from the image region that contains the car. And because of the fact that the luminosity of each region differs, the location of the histogram peaks also changes depending on car location. This results in that the location of the peaks in the sound spectrum changes depending on car location. So try to listen to the video that is presented next to see how the sound brightness changes depending on car location. The operation of the algorithm is visible in this figure that presented this slide. In this figure we can see the long-term spectrum of the generated sound from each image region, taking into account only the intervals in which the car was in a given region. So the different lines correspond to different image regions, so there are 12 lines here. We see that the location of the spectral peaks, they have these 3 peaks here, it changes depending on the region in which the car is moving. For example, when it is in the 12th region, so the location 12 as we call it, the center frequency of the third peak is significantly below the central frequencies for other locations. Some smaller differences exist for the first peak, and also there is a lag for a first peak for this particular image region. So in general, the result of applying the algorithm is that the peak central frequency and amplitude depend on the luminosity of the area in which the target moves. This essentially results in a luminosity to sound brightness mapping. The next step is to perform an evaluation, a first evaluation of the possibility to track object location based on the location of the peaks in the sound spectrum. In the experiment that we are going to present, we use the dual task setting because in these cases we expect to have a benefit from sonic output. The task was to track the location of a moving target and report when the target moved into a monitored area while transcribing text. There were 2 independent variables. The first was monitoring display modality and manipulated the modality in which users monitored target location. This was either auditory or audiovisual. The second was monitoring display location. This manipulated the location of the users relative to the monitoring display. When frontal, the display was in front of the users, and when dorsal, it was on their back, which means that they had to turn to see the video stream when this was available. Dependent variables were monitoring and transcribing speed and accuracy. We hypothesized that the difference in the location of spectral peaks will allow users to identify when the car entered a particular location. We also hypothesized that location monitoring performance will drop and confusions will appear for locations that have a similar luminosity to the target one. And also we hypothesized that monitoring performance will deteriorate for audiovisual presentation when display location will be reversed, when modality is audiovisual, but not when auditory, because users will have to turn to look at the screen. Here's the experiment setup. You see here that we have a dual task setting. And on the left of the image, you see a user that is sitting, a user sitting and ready to perform the experiment. You see that the user is sitting in front of a desk, and there's this bookrest which contains there is the text that will be transcribed. There is also a computer keyboard and a screen that is used for transcribing, and on the back there is a projection canvas on which a video of the moving car was projected when modality was audiovisual. Behind this projection screen there was a loudspeaker that played back the sound from the algorithm. When location was reversed, the transcribing setup and the user were rotated 180 degrees, so that the canvas was on the back of the user. The location monitoring task was to report when the car, so the target in this case, entered the marked location. This is location 12 in the graph shown before, and is drawn here visually in this image. I want to mention that this frame was visible while the experiment was running, whereas the video was only visible in the audiovisual condition. In the auditory condition, only the frame was visible. Participants were instructed to transcribe as quickly and accurately as possible while reporting when the car entered the target area by pressing the one key, and there were two groups of 10 participants in the experiment. In this slide, we can see the monitoring performance results. The figure on the left shows the hit and false alarm rate. We see that the hit rate and false alarm rate are higher, so hit rate is higher and false alarm rate lower when modality is audiovisual compared to auditory for both locations. However, there is a small increase in false alarm rate for the audiovisual modality, which was when location was reversed, which was significant. On the right-hand picture here, we see the spatial distribution of detection frequency. We see here that for these two locations, we have a significantly higher possibility that a false alarm appears. And these are indeed the locations for which the luminosity was matching or was closer to the target location luminosity. On this slide here, we have two more graphs that show monitoring sensitivity versus monitoring speed and transcribing performance. So on the left-hand side, it's monitoring sensitivity on this axis and monitoring speed on this axis. We see again that sensitivity was higher for the audiovisual condition compared to the auditory for both frontal and dorsal display locations. We see, however, that there's a deterioration in speed for the audiovisual condition, which turned out to be significant, whereas this result here, the deterioration, was not significant for the auditory condition. Furthermore, we see, and this is the most important effect of location, that there is a significant deterioration in transcribing speed and accuracy. So we have transcribing speed here and accuracy here when location is reversed and modality is audiovisual. So this is this big difference here, which is so significant compared to the auditory case where there is no significant deterioration in transcribing performance. This finding essentially shows that participants strive to use visual feedback despite the presence of sound when location was reversed, and in doing so they penalized transcribing more compared to monitoring, for which the effect of reversing location was relatively small when modality was audiovisual. To conclude, the hypotheses were overall confirmed, as participants were relatively successful in identifying target location based on the sound generated by the algorithm. However, confusions increased for areas of similar luminosity as it was possible to predict. Furthermore, reversing location reduced transcribing speed and accuracy, and monitoring speed, and increased false alarm rate when modality was audiovisual, and none of this effect appeared when modality was auditory. However, this benefit is not so easy to apply because monitoring performance overall remained lower for auditory compared to audiovisual monitoring, which may limit the applicability of this result. In conclusion, I presented an algorithm for auditory location monitoring, which changes the sound timbre depending on the location of a moving object in a moving image stream. I showed that even though users were relatively successful in using the sound for recognizing when a moving object entered a particular location, auditory location monitoring performance remained below audiovisual. Thank you very much for your attention.
Hello, I am Marco Tiraboschi from the Music Informatics Laboratory at University of Milan, and I will be presenting the approach we developed for spectral analysis for modal parameters linear estimate. Our aim was to develop a computer-aided system for sound designers to help them find the modal parameters for impact sounds of unknown objects. The need for this tool derives from the fact that a lot of modal parameters are needed to obtain a high-quality modal sound, so that doing this manually will require a lot of time. Our approach is based on a single audio example of the target object to be modeled, and no further information of the object is needed. This was a constraint we put so that if a sound designer hears a sound that he wants to recreate, he can do it easily without inputting any information about the geometry or the materials of such object. Our method is built upon spectral modeling using linear and also non-linear techniques for regression. There are two main categories of modal parameters estimate for audio. The first family is that of geometrically informed approaches. These approaches exploit information about the geometry and the materials of the objects to be modeled in order to obtain the modal parameters. Having knowledge about the geometry and the material of these parameters is a reasonable assumption, because often these techniques are used in virtual environments where we have the mesh of the object. Also, information about the geometry and the material of the parameters can be combined with audio examples to improve the estimate, and these are hybrid approaches. There are also fully audio-based methods, and our approach is a fully audio-based method. These methods can be used when we do not have the mesh of the object or we do not know the parameters. Our method uses spectral modeling synthesis. In particular, uses the analysis framework for spectral modeling synthesis. It is mainly based on two components. The first component is a peak detection algorithm. This is based on the short-time Fourier transform of the signal, and is based on take the magnitude prominence of the peak, and also consider phase flatness to detect peaks in the short-time Fourier transform. Then there is a peak continuation algorithm that organizes peaks in trajectories in the time-frequency domain, so that each trajectory can represent a partial of the sound. We added some more steps after the sinusoidal modeling synthesis analysis, and those are splitting the trajectories into smaller trajectories that have almost constant frequency. This is based on the assumption that in impact sounds, frequencies are mainly constant. This is not always true, but this is the case we are considering. After splitting trajectories in constant frequency trajectories, we regrouped trajectories that have the same frequency. Then, since we know that in impact sounds all the sound begins at the same time, we can discard trajectories that start later. Also, we obtain better results by inputting the audio in reverse over time. This is a very common trick used in analysis for additive synthesis. The mathematical model behind our approach is that of linear model analysis. We consider the sound as the linear sum of different partials. Each partial is a sinusoid that has a starting amplitude and then is modulated in amplitude with an exponentially decaying envelope. The frequency of the sinusoid can be time varying, even if in our model we assume that it is constant. The starting amplitude is determined by the point on the object, so that a partial is actually a function of both space and time. In our model we only have one audio example, so we model only one pickup point, so there is no space dependency. Based on this model, we can consider the trajectories that are output by SMS as the time series of the couples of instantaneous amplitude and instantaneous frequency. To derive the modal frequency, since we assumed that the frequency is constant, we can just take the average of the frequency in the trajectory. To derive the magnitude and the damping parameters, that are the parameters of the exponentially decaying envelope, the magnitude is the starting amplitude, and the damping is the time constant that determines the time scale of the exponential. We can consider the fact that if we take the logarithm of an exponential function, we get a linear function. So we can apply linear regression on the amplitude of the trajectory of the partial to derive magnitude and damping. If there is some noise at the end of the trajectory, we can observe that the instantaneous amplitude has this kind of hinge function behavior. A hinge function is a function that decreases linearly up a certain point, that is called the knee, and after that is constant. We can fit the magnitude and damping parameters using this function as a model in order to reduce the effects of noise. So we initialize the magnitude and damping parameters using the parameters we found using linear estimate, and we initialize the knee point at half the time scale of the signal. Then we run nonlinear least squares optimization. After estimating frequencies, magnitudes and damping parameters for each of the partials, we can evaluate if those parameters are realistic or not. A first constraint that we can impose is that the decay parameter must be positive. If the decay parameter is positive, then the exponential is decreasing. If the decay parameter is negative, then the exponential is increasing, and this does not correspond to an impact sound. For evaluation, we used a dataset of 80 sounds. They are 20 samples for each of 4 objects: a glass bottle, a mug, a saucepan, and a wooden stick. We evaluated our approach by resynthesizing the sound using the sound design toolkit that has some modal synthesis functions. We evaluated our approach by resynthesizing a sound using the sound design toolkit, and also compared the performance of our approach against SDT's own modal tracker. We performed an objective evaluation computing the Pearson correlation coefficient between the first 12 MFCCs of the original sound and the resynthesized sound using our approach and SDT. You can notice that our approach is significantly better than SDT for all MFCCs except MFCC number 7. For MFCC number 7 there is no significant difference. Also, we computed the normalized Euclidean dissimilarity because the Pearson correlation coefficient does not account for scale. So we wanted to evaluate another metric that accounted for scale. You can also see that for every MFCC except MFCC number 7, our approach is better. We also performed a subjective evaluation. We used one sample for each of the sounds in the original dataset, and also added 5 Bells samples. They were added because the 4 sounds that we have from our dataset were very short sounds. This was good for the objective evaluation because they were quicker to analyze, and also SDT's modal tracker works better on quicker sounds, so it was a fairer comparison. But we also wanted to evaluate our model on longer sounds. For subjectively evaluating the performance of our approach, we used the Marshall framework. So for every sound, we presented the user with the reference, that is the original sound, and 5 tracks that the user had to score. Hidden in the 5 tracks, there is also the reference. There are also 2 tracks that are obtained from the reference and are low-pass filtered at 7 kHz and 3.5 kHz. The 2 remaining tracks are the 2 tracks resynthesized with SDT using the modal parameters found using our approach and SDT's modal tracker. Overall, we had 12 participants, but we discarded the scores of 2 participants because those 2 participants did not recognize the hidden reference in 2 examples. Overall, the reconstruction quality obtained using our algorithm has been scored as fair, which is also the same as the 3.5 kHz filtered reference. It is significantly lower than the other references, as we could expect, but it is significantly better than the performance of SDT, which has been evaluated as poor. Now we can hear a couple of sound examples. In conclusion, our approach requires no previous knowledge of the object geometry or materials, and also requires a minimum of one audio recording. The limitation is that our approach is only applicable on linear rigid resonators. If the resonator has a very nonlinear behavior, then our approach is not the correct approach to use. Also, it's not very robust to external factors such as reverberation, even if the nonlinear regression attenuates these problems. Another limitation is that the system is modeled as a whole. We are not disentangling the sound properties of the resonator and the impacting object. Also, we are modeling the sound at only one pickup point. For the future, we are working on implementing directly the assumption of modal analysis in the SMS framework, so that there will be no need of splitting the tracks and joining them back together after the analysis, and this should reduce the execution time of the algorithm. Also, we are planning to develop a GUI so that people who do not want to use the Python API can just use that. Also, that GUI should provide functions for human fine-tuning of the parameters extracted automatically. There are other directions that we can take from this point. One of those is of generalizing for more than one audio example. This could be done, for example, by performing linear regression or nonlinear regression on the corresponding trajectories that we extracted from all the audio examples and correspond to the same partial. Another direction could be that of exploiting the information derived from geometry and materials of the parameters if it is provided. Also, it would be useful to include a model for partial beatings, because at the moment, if there are beating partials and they are not resolved in the timescale of the STFT, then they are modeled as one partial, and we use the realism of the beat. Also, we can try and infer some information about the impact interaction from the stochastic component of the signal, that is, the residual component that we get when we subtract the sinusoidal component. All the code that we used for developing and evaluating and testing the approach is available on GitLab. Also, at the same repository, you can find Docker images for executing the scripts. And also on the GitLab pages website corresponding to the repository, you can find documentation for the code and also all the audio that has been produced and all the plots that have been produced. There is also a pure data patch that allows to use the parameters that can be extracted in Python with our approach into pure data using the SDT library. Also, before concluding, I have to thank the SDT team because they showed a very high interest in our work, and that was very appreciated. And we invite all of you to listen to their presentation that they're doing for this conference about modal analysis for non-constant frequencies. Thank you for your attention.
Good afternoon, I am Argan Verrier from Sorbonne University, Paris, and I am here to present you an interactive software for the sonification of neuronal activity. There are 86 billion neurons in the human brain, and we are only starting to understand how these neurons are connected and how they function to drive movement, emotions, and cognitive abilities. Recently, the zebrafish has become a popular model system to study brain functions, as there are only 100,000 neurons in the larval brain. When a neuron is active, there is an increase in calcium levels. By recording a genetically encoded calcium sensor, GCAMP, we can monitor brain activity as the calcium ions bind to GCAMP, causing the protein to increase its fluorescence intensity. This technique is called calcium imaging and is especially powerful as it allows the monitoring of real-time activity in as many neurons as can be imaged under a microscope. Because the zebrafish is transparent, we can easily record and monitor neuronal activity using this approach. Here is a recording of hundreds of neurons in the zebrafish habenula, which is an evolutionarily conserved area of the brain that responds to stress, anxiety, or fear. By measuring the changes in its fluorescent level, we can monitor neuronal activity. However, due to the large number of neurons, it is difficult to find the best approach to recognize the different types of activity in the brain. This work was initiated to find a novel method to more easily recognize and differentiate the diverse activity of hundreds of neurons. The goal of this project was to study if sound information in addition to visual information would help clarify the different types of neuronal activity. We designed an interactive software to facilitate the best method to amplify the fluorescent changes we recorded based on the temporal and spatial pattern and synchronized activity. A special attention was given to the ease of using the software and the aesthetic aspect of the sonification. Therefore, the software was implemented as a Maxi-based patcher, which consists in an interface and a video design. The data we used were acquired using calcium imaging of the spontaneous activity in habenular neurons in the brain of the zebrafish larvae. The calcium imaging was performed using a spinning disc microscope at the rate of 5 Hz. The recording was then manually segmented into regions of interest, ROIs, which roughly represent neurons. So we finally have the average fluorescence within each ROI, which we call the signals of the ROI, the location and geometry of the ROIs, and the cluster group of the ROIs, which were obtained based on their correlated activity patterns. The sonification is based on a manually drawn ROI. Each ROI is represented by an FM synthesizer, whereby the carrier is obtained by reading a wavetable at a pitch frequency Hc, which we call the note of the ROI, and this frequency is modulated by a signal obtained by reading another wavetable at the modulating frequency Fm. The parameters of the synthesis are driven by the properties of the signal of the corresponding ROI, and the sound that comes to the user is the summation of the signals produced by each ROI. The user interacts by making groups of ROI, setting the mapping parameters, and choosing notes and wavetable. The amplitude is mapped to the preprocessed and normalized signal of the ROI, its first derivative is mapped to the inverse of the harmonicity ratio, the location is mapped to the panning, and what we call a group parameter drives the modulation index. The group parameters are introduced to provide additional information about the group of ROIs, such as the average fluorescence intensity in the group as an example. I will get back on this later during the talk. On this slide, you can see the three main parts of the interface. A window, which displays the recording and the ROI, represented by the colored dots. The main panel, where the user can choose the node to use, allocate ROI to the group or remove them, manage the data and the video and audio feedbacks, and access the other part of the interface. And this panel is the mapping panel, where the user can access the parameters of the sonification, such as the parameters to use to drive the modulation index, the scaling of the parameters, or the choice of the normalization method. Here is a quick demonstration of the results using cluster main groups. Due to the background levels, differences in the amplitude and the range of the fluorescent signals, the first step is to preprocess and normalize the data. The software enables the user to choose the method to preprocess and normalize the data prior to the sonification. We implemented three preprocessing methods: the standard deviation and average, which compute the deviation from the mean value of the signal, normalized respectively by their standard deviation or mean value. The last method is a running average computed over a number of frames chosen by the user. Here are the results using the standard deviation, which is very similar to the average. And here are some results using the running average computed over 7 frames. As we can hear, the signal tend to be smoothed too much, and some activation are missed, which is an issue as we are interested in detecting the variation within the signal. In addition, 3 normalization methods were implemented. The first normalizes the signal frame by frame by the maximum on each frame. The second normalizes each signal with the overall maximum in the whole recording, and the last normalizes each signal separately by their maximum over the whole recording. Here is an example using the frame-by-frame method. So as we can hear, the variation between the frame tend to be smooth, and the activation tend to be barely audible. And lastly, here are the results with the maximum per array. So this method was the most largely used, as it kept intact the variations between the signal and do not emphasize variation from array to another. We were able to identify the ideal parameters for the preprocessing and normalization step by comparing the audio and visual information simultaneously. Usually this is carried out by comparing graphs generated from the recordings, which require going back and forth between 2 visual media. On the top, you can see the part of the mapping panel associated with the mapping to the modulation index. The parameter used to drive it can be chosen by the user. It consists in a value which can be the fluorescence or its rate of change, and a method to process the value. For each frame, the parameters are computed for each group, and therefore is the same for every array in a given group. Thus, for each frame the values are routed to the appropriate group, then the parameter is computed and scaled to be used to drive the modulation index. 4 processing were implemented. The first one is the average value in a group or its rate of change. So as we can hear, the sound gets brighter when the group is highly activated, or when the mean value increases. In this case, we have used cluster group instead of individual arrays, as we wanted to focus on how well the neurons are synchronized within the cluster groups. In the case of user-made groups, the less homogeneous activity would produce a less bright sound, and the quality of the result largely depends on the groups. The activation ratio computes the ratio of non-zero values provided over the total number of values provided. Here is a sample using fluorescence as the value and cluster-made groups. As we can hear, either arrays are synchronized and become activated at the same time. A very bright sound is produced, with good variation. On the contrary, if only a few arrays are activated randomly, a more constant brightness is produced. Therefore, we use this mapping to get information about the synchronicity of the arrays within the group. We can also use the standard deviation of the value provided for each group. The resulting sonification is not intuitive, as if the neurons within a cluster are active at the same time, the sound gets less bright, while it is brighter if only a small number of arrays are active, which was thought to be less intuitive. Finally, several comments can be made on the effect of the chosen notes and sound. Initially, we distributed the note on a C major scale rather than random frequencies in order to keep an overall consonance. An interesting point was the effect of the interval between the selected notes. Different intervals were tested. First of all, when using small interval, up to perfect fifth, consecutive activation were more easily perceived as melody, such as with this set of notes. On the other hand, if I chose larger intervals, the activations are more likely to be perceived as independent events. This phenomenon of steering by pitch proximity was used to monitor temporal pattern of activation between the groups. Another point occurs when selecting low-pitched note. In this case, the synthesis produced what can be perceived as two auditory streams, one with the note themselves and one with the high harmonics added by the frequency modulation. This effect was mostly used along with mapping that produces very bright sound, in particular with the modulation index driven by the activation ratio, to differentiate information about the neuron and about the groups. Lastly, the first requirement was to obtain a uniform relationship between perceived loudness and selectivity, regardless of the tone selected for the group. We thus use isosonic curve to map the activity of the RI to the amplitude of the audio synthesis. To conclude, we developed an interactive sonification software using parameter mapping to explore neuronal activity using calcium imaging data. The mapping to the amplitude appears to enable the recognition of temporal pattern of activation, and the mapping to the modulation index appears to provide additional information. However, the results largely depend on the choices of the user, especially the setting of the interpolating curve and the choice of the parameter to the modulation index. The selection of notes also had an impact on the perception of the sonification. This point would require further research. Based on these results, we designed 4 presets that you hear throughout this presentation. A default preset less sensitive to the dataset, a preset intended to be used to monitor RI activity, a preset intended to monitor the synchronicity of the RI within the group, and lastly, a preset to monitor temporal pattern of activation. Finally, the sonification of the visual media appeared to enhance and clarify the visualization of neuronal activity. In particular, the addition of the sonification appeared to be useful to choose the normalization and preprocessing methods. These conclusions should be completed with further studies. In conclusion, we have made an interactive software which can be used as a tool to further comprehend the diverse and complicated mode of neuronal activity. Thanks for your attention.
Hello, I hope you all can hear me. Hello from the heat wave in Stockholm and welcome to this Q&A session for the SMC oral session 6, focusing on sonic interaction design. My name is Emma Frid and I would like to begin by thanking all of the presenters, and we will now open up for questions from the audience. I first have a question for Marco. And the question is, could you go into more detail how reversing the audio helps in analysis?
Yes, so In musical sounds, especially in the case of impact sounds, the sound can be viewed as the sum of two different components, so a stochastic component and a sinusoidal component. We are interested in analyzing the sinusoidal components, but if we process the sound in the correct order of time, we first encounter the stochastic component in the transient. So by processing the audio in reverse order of time, we can process the sinusoidal component first, and this allows the algorithm to pick up the correct partials first. While if we encounter first the stochastic component, the peaks may be chosen at random from the stochastic component.
Okay, thank you. And then we have another question from Davide Rochesso. It's a question about computational costs. Is nonlinear regression the heaviest computation? And what's the general cost of the system after the short-time Fourier transform?
So actually, nonlinear regression is very lightweight in this instance because we have a very few data points, so it's very quick. Most of the computational cost of this system is from joining back the trajectories together after splitting them, because you have to try the different combinations. So it's combinatorial. That's why we're trying to implement the model assumptions directly in the analysis framework so that we can avoid joining back the trajectories together.
Okay, thank you. And then we have a question for Argan from Adrian. Can the data be accessed by other applications, such as, for example, pure data?
Yeah, so the data we use for the sonification were computed using the software Fiji and then formatted using MATLAB script, just to be used with Max MSP. But yeah, I think they can be formatted to be used with other software such as Purge Data. Yeah.
And then I have a question. Can you describe the properties of the data that makes it more suitable for sonification as opposed to only a visual representation?
The main thing we observed was for the normalization part, the idea was that usually the choice of the normalization in preprocessing is obtained by comparing two visual media, whereas in this case we compare a visual media and an audio media, which was thought to be easier. And we also observed that the addition of the audio information will help perceive the consecutive activation of the different clusters of neurons.
Okay, thank you. And you also mentioned in the paper that aesthetics was an important aspect of your project. Can you elaborate a bit on that?
Yeah, so the first aspect of the aesthetic part was to use notes instead of a random pitch note. We thought it to be a little bit easier to hear, and also setting the different scaling and the different parameters to achieve something that was easy to hear and easy to understand. For example, not having a sound that is too bright or something like that. Yeah, that was a goal of the project. Thank you.
Thank you. And then I wonder if we have anyone in the audience who has a question for Yorios for the paper Picturize. Okay, there's nothing in the chat so far, but I have some questions. I'm wondering how you think that the results were affected by the fact that the participants in the experiment had no training when it comes to critical listening.
Yeah, well, I think that that affected some of the participants. So there were about 3 of the participants that had quite low performance. And then from the rest of the participants, there were 3 or 4 that were almost at 100%. So I think that with some training, it could be that the results would be even better. Yeah.
Maybe I missed it in the presentation, but are the sonifications or videos of the sonifications available online?
No, not yet, but I can make them available. Yes.
Would be nice.
If you like to have them, yes.
Yeah. And how would you say in general that your work stands in relation to previous research on sonification of images and pictures, and how is it unique compared to the previous research?
Well, I think the main point here is the use of the histogram of different image areas. So this is an addition to what has been done before. So, and this creates essentially this luminosity mapping, so image luminosity to brightness mapping that can be used and extended also if one takes colors into account, for example, the different so RGB channels and so on and so forth. Yeah.
And what is the next step of this research?
So for me, it would be more to focus on using color in the sonification, and so not working with grayscale, but using different color channels, hoping that this could add more cues for the users.
Okay, we have another question, but I'm not sure who it is to. So if the person Giorgio Presti could specify to which author that question is directed in the chat, that would be great. And I can meanwhile ask Marco what the next steps of your research is.
Well, I think that the next step for this research would be to provide an easy GUI to use, because we wanted to make this method available for sound designers, and the most easy way to do so is via a GUI.
Thank you. Do you have a reply from Giorgio? The first presentation, okay. So Giorgio is asking, did you try with different scalings of distributions, for example, log or linear in frequency and amplitude for the first presentation? No? So the first presentation as in to Giorgio's, I'm assuming?
Yeah, that's fine.
Did you hear the question?
Yes. So if I try different scalings of the distributions, no, I have not experimented with that, I have to say. So it was, no, I have not tried this out.
I'm wondering if we have any other questions from the audience. I have one final question for Giorgio. I'm wondering what the applications are of this the system, if you think of any other applications for the translation of.
So I think for me, so the applications that I see is mostly for situations where you need to monitor people or dependents without, so in general, slow targets that do not move a lot, and it's very tiring to look at the screen every now and then, so to check them. And therefore, so I would think them like as additions, for example, to like a baby monitoring system, or so something more like in this direction, where you can notice where different targets move and when they enter different areas. So that's like the main or one application area.
I have, if there are no other questions from the audience, I have a final question for Marco. I'm wondering how you selected the different objects and the materials for your experiment.
Well, I used those objects because we had a data set of sounds of those objects recorded in the laboratory. So those were the sounds that were available to me. And I used the main dataset for the objective evaluation, and then I chose some other sounds that were different for the subjective evaluation.
Okay, thank you. If there are no other questions from the audience, I would like to thank all of the presenters again. And Yes, no other questions in the chat? No? So thank you all of the presenters and the authors of this session, and have a nice the rest day of SMC.
Good afternoon, everybody. This is a presentation called Sound Space Kinetics. My name is Marek Holoniewski. I'm from Kraków, Poland. The special presentation for CMC conference in Torino, June 25, 2020. Sound space kinetics, it can be presented using three basic keywords: metaspace, transgressive, and biosensoric. Those are the three elements which will be presented during my presentation. I want to show you the list of projects which are either reference and very close to art utopias, temporary suspension, frozen in virtual space, approximative simulations of performance. There are a list of different projects, some of them which are shifted to the left margin. They are utopic projects, never realized. Since they are including quite controversial elements, they are still on the way to be arranged and performed in the future. Some of them are linked, so if you get the PDF presentations later on, you can visit them. Description is in Polish, but the most of the titles are in English. Let's go to the concept of meta-instrument. Meta-instrument is described by my concept as a movement of people and object in a space, which describes a new model of active sound space. Acoustic resonance of traditional instrument generate vibration of a space. So I explained the vibration of the space is the most important element of the concept of meta-instruments. Listener, receiver becomes in this way part of the instrument, active, vibrating, also in 3D space. So in fact, there's no really big difference between a real or virtual space in my concept. To come back to the very basic routines, the listener receiver can be passive in case of installation, or it start to be active in case of interactive installation. Meta-instrument can be also described as a space and its resonance. So in fact, it became a part of kinetic space. Kinetic space can be described as a movement as a sound source. And when we really try to understand the concept, we are mainly starting from the gesture as a main movement in space. It can be in a traditional, in a music sense, it can be instrumental, also conducting, but it can be dance-like or performer-like, with a special reference to the performance art concept. But when we go further, we can also consider the movement of people and objects. Then it can be active, as described before, passive, or consecutive. Consecutive, it's a very special form where we are translating several instructions and we code them to more complex and effective idea. I will describe it later on the series of example. Then we are talking about special scales. The scale which is quite important for my project, a scale which is like a large global scale. In this case, I call it macro. And then micro, which is a very special reflection or conversion of or translation of certain elements of macro space. In this case, we have the a special activity in traffic, in urban traffic, open spaces. Then we are talking about different mapping strategies. Then one of my favorite terms is transgression, when we are moving from one model of space vibration to another one. We are using a special translation method. It will be described later in certain examples, much more detailedly. Then network interaction, which use the previously explained strategies like trapping, mapping, and transgression, and a very special example and special use of meta instrument is when we are composing, when we are arranging, when we are managing a network interaction. Then another quite interesting focus is the cases of vanishing spaces, the spaces which disappear, which start to be not quite clear and transparent. And on the end of my presentation, you will get certain examples of this. Sensoric deprivation is also just between transgression and vanishing spaces. We are talking about certain kind of phenomena when we reach the edge of our sensors, when we are really losing clear and then on the end we have neural networks, which are quite special case of art activity, which are in microspace, but also they're inside a very specific ephemeric and metaphysical space, which are both virtual, physical, and subconscious space. Then we go to the certain examples, like my early works with the light button, light conducting, a piece called WISIC, what you see, you get. Those 5 letters describe the concept, from 1989. As you see, there are certain arrows showing the movement of sound according to the gesture. When the light is moving from left to the right, the sound is controlled live by the movement of the light. In fact, I'm using 4 optical sensors, photocells, attached to my face. 2 of them are near my ears. They are responsible of the space movement. 1 of them are on the neck. When I go vertically down and up by the light, then I control so-called orchestration. I'm moving through different models of processing of sound transformation. The most important is inside my mouth. This is a time triggering sensor, which triggers the tempo. It triggers amount of events splitted or exploded from my mouth. Let me check whether we are ready to show you the short examples here. Next example is Dark and Light Zone from 1999. The piece composed as a commission for RTT Quartet. In fact, I built up a special light installation based on 4 light sensors, where I control 4 virtual instruments by the movement of my hand, 1 or 2 hands, and then the structure are controlled live in a way that I'm thinking about the 3D sound sculpture around the light and around 4 sensors. Then the last example is the example of my performance presented it 9 years ago on TEDx presentation in Krakow called Invisible Instruments. So there's a complex of different models of interactions, mainly generated by the composed material in part, and in other part controlled live. But some of them are instrumental sound, orchestral structures similar to the timbre of orchestra. The other one are abstract synthetic sounds, which are mixed up together. Some of them are blended in a space. Then there are a series of objects on the picture. You see two chopsticks, which are used like two conducting buttons, which are conducting the virtual orchestra, flickering, vibrating, moving up and down. Then the next example is quite interesting example of 6-channel audio system attached to the sound installation called Ears, Eyes and Nose. The piece arranged, composed, designed together with my friend Marek Landa. So he was responsible of the visual aspect of the space. Here you are. That's the performance of Giannozzo Gallery in Berlin. The piece was realized quite long ago, 1988, and performed an exhibit in many places in Poland and in Europe. Then we are going to the example of active object rotation. This is the first example of the work by my student, Maria Olbrechtowicz. The piece is called Mach, consisting from the large metal plate with contact microphones and transducers. The metal plate vibrates because of the physical feedback between those devices. So the metal plate start to be vibrating. It depends on the position of the transducer and the contact microphones, but also the way we are touching the plate. So in fact we are playing on the vibrating plate, and that's the basic way we are using the instrument. But in fact the most important element of the installation is rotation. So in certain moment the plate start to rotate, changing the position and changing also the sound it produces. The sound is harmonic, inharmonic, noisy, quite large and giant. And we are, in this case, in the case of by Maria Olbrechtowicz called Mach, that's mainly the matter of speed of rotation. 2013. Then we go to the series of project which I listed here on the slide, and that's part of my concept global and net art projects. The first project initiated in this list was done in 1983, the telephone concert. Then there are some other either net art project or macro scale outdoor projects like Art Boat, so the boat moving from one city to another one, or a virtual net art project, which is GPS art, both initiated in 2000, using really different selected devices. You have the links, so we can go to the website of those projects later to get more familiar. Quite interesting is Global Terrain, also described later. Ether, the virtual project based on the large library of Polish Society for Electroacoustic Music, but also for the library of International Confederation of Electroacoustic Music. The project initiated 2013, and it is still available on the net. Then the quite interesting series of projects are brainwave, call it by me, brainwave networking, and especially the one example here documented is Double Brain with two performers linked, connected by biofeedback technology on the large distances using internet and special individual channel to get control, bidirectional control. Then 2017, Wind Waves, the piece for orchestra and electronics, and then the last piece done with Chris Cutler from London, Formati, Folded Maps of Time. So let's describe a little bit some of them. Metakinesa macro network performance. Here is a diagram of telephone concert. 3 cities interconnected by telephone line. Warsaw, Wien, and Toronto. In Vienna, Warsaw, and Toronto, we have 3 spaces connected together with one ensemble playing live and 2 other rooms with the audio system getting the performance from the other 2 cities. So this is the triangle and the connection, which was quite interesting because we've got quite affected connection over the telephone line on the international call without delays. Quite reliable and quite interactive. And then we go to the example of Artboat. The project never realized, initiated in 2000. We have different elements of the project. In fact, the one of idea was to invite many artists to open the big collaborative project, and the integration of the improvising scene, the free improvisation scene, quite active already in this time in Poland, and the performance art activity. So I invited them all to the boat, rented boat, which were moving from Kraków to the north of Poland through Vistula River, our biggest river. By weather and physical logistic circumstances, the project was never realized. We keep it on hold for 2 years, but finally we have to postpone it for unclear date. But the project is developing itself. It's like a project in a second life. So it's quite interesting to go to the website and to check how does it work now. Then we have the quite important issue, which is GPS art activity. I opened GPS art activity in 2000 by landing on an airplane. I saw my city, Kraków city, in form. Well, you have the map of the city here on the left, which looks like a piece of pizza. So I've got this crazy idea to cut the city map by slices and to work with all those regions separately, getting different zones, different audio recording on the beginning. So in this case, the city became an audio and video sampler, city sampler, containing hundreds of recordings. On the beginning, all those recordings were indicated by points of interest, so the coordinates basic for GPS system. Later on, all those recordings were loaded to the server, and then the car was became a main performer car with GPS, GSM internet system connected together in 2001 became a main performer of the project. You see the diagram of GPS technology, you see early mobile phone and my early black power book. Then the region we were moving and we were exploring. So small ring of Krakow called Planty with the Wawel Castle here and the big ring around. So that was the zone we were exploring during this project mainly. Here you have one of the early patch, Max MSP patch in Macros 9, designed with those colored dots of the satellites above the northern hemispheres. And then you have another part of the patch when we are calculating the movement of the car, crossing certain streets with certain recordings attached, connected. And then the car was in fact initiating the previously recorded audio material. That is the quite interesting concept of a city and creating the continuous structure as a mix between different regions of the city. Then we go to another project by another student of mine, which was initiated and inspired by GPS art. The project is realized in the blackout space. Timofey Maximenko, the Ukrainian artist living in London or in Valencia before, he created with my direction. He created a blind map sound labyrinth. So in fact, we are in a blackout space, listening and navigating a sound by touching and tapping for color knobs, which indicates front, back, left, right. Then we go to the quite interesting project based on and with a very special reference to wave field synthesis, the method invented in IRCAM, developed and arranged in different other centers, including Technische Universität in Berlin. So here you see the principle. Here you see some of the rooms with hundreds speakers, which are a very special arrangement controlled by cluster of computers, but which was a very special influence to my project called Vertical Orchestra from 2008. I tried to build up an acoustic wave field synthesis. So in fact, watching to the buildings in the night, I found out that there are quite interesting blocks, there are quite interesting vertical surfaces. And then I discovered that when I put the academic orchestra, the orchestra of my Academy of Music, distributing them in a way that each musician will be located in one window of all rooms from the front wall of the building, I can put a third dimension, a vertical dimension of the orchestra. So try to imagine, usually we listen to the music, to orchestra on the flat surface, only getting the sound trajectory in an ambient space, left, right, more or less. It can be quite nicely the space considered when we are talking about topophonic concept in the second half of 20th century. There are several examples like Topophonica by Bogusław Szefer, but also Jean Chet by Yanis Xenakis. But in fact, for me, it was quite interesting to consider this aspect to build up a virtual, a vertical stage. So to lift the stage, the traditional stage, up to lift them up to see the musicians. So the loudest instrument on the backstage, they are shifted on the highest level, while strings are on the ground and the first floor level. The project were never realized, so it is part of the utopic group of projects. Then we have the quite interesting project Motus Interno together made with Miłosz Uczyński, a great DJ artist from Paris. I made the music for this project. The project was built up from the organic elements planted before in advance, and then with beautiful video images we performed this on a real set of building front in Cascais in Portugal. Then we go to the project Global Terrain from 2007, spheric string, live global network. Try to imagine that we have a maquette, we have a ball with the diameter of 18 meters, and we go inside. When we go inside, we see the continents and the oceans around us. When we direct a finger to certain point of the continent, we open a live webcam of different locations. So the idea is to make a opening and mixing of different webcam windows. So that is the essential idea of another utopic project never realized, Global Terrain. So in this way, I'm thinking about a globe, about the Earth as a large global surface, and we put on this a small ball, which is just a copy of the real globe. And then you see the different representation of the project, and then the visitor is inside the globe, controlling different points of different continents. Let's move to the short example of the solar system and Astrolab, the astronomical device instruments, the beautiful project by my student Piotr Madej from 2017. All those projects were realized during the regular program on intermediate department, Fine Arts Academy in Kraków. I'm teaching at the Academy of Music, but also at the intermediate Fine Arts Academy in Kraków. So the solar system is used in this space like as a musical instruments, quite advanced, beautiful project inside the spheric space, controlled by the copy of Astrolab. Replic of the historical ancient astronomical instrument device. Then we go from macro to micro, macro to micro scale. So then we go to those key words mentioned on the beginning, like metakinesis, micro transgression, crossing conscious boundary towards some conscious. Cerebral cortex. Cerebral cortex is a quite important issue. So here you have the from 2014. I'm working intensively using biofeedback devices. So EEG, Neurosky Mindwave mobile device from brainwaves monitoring. So the list of pieces using this technology, and then quite important is the double brain, the project made together with my former student Franciszek Karaczkiewicz. We are interconnected by two brain monitors, especially when we are quite large in the physical space. So whenever I'm in China or in Mexico, US, we are dealing with this project, so that the physical distance is quite large, but in fact we are connected our brains together, and we are controlling projects live, controlling different media, sound and video all together. So there's a list of performances here. 9 performances of Double Brain were already realized from 2016 to 2019. Next project is by my student 2017, Me and You equals am. This is the title translated to English. Biofeedback plus virtual reality VR goggles. So you see there are two cells, two rooms interconnected. The first person controls the abstract images, abstract structures, while the second one receives, but then with the controls this virtual space, and the result come back to the first one. So in fact, this is a bioneural feedback between two persons working together. Quite interesting master diploma by Łukasz Furman. Then the series of three pieces from 2017 till 2019, new elements like reactive scores, mapping, acousmonium, sensorium, biofeedback, tactile. You see the reactive scores which are built up live by the orchestra. That's the structure of the piece in Polish, but you see 6 waves, vertical, horizontal, tidal waves, entropy waves, rotation waves, and neural wave on the end. A quite large piece, 1 hour large. Then another piece also for the group of soloists, amateur teenagers, which are used as alternative performers, audio and video mapping. Quite interesting. That's the diagram of the piece. You see, you have also the link to those places. Here, the last piece, together with Chris Cutler, I built up the concept when we are divided ourselves for 2 hemispheres of brain. I'm controlling one video representation of the video and laser representation of hemisphere, and Chris Cutler controls another one. We are playing together, integrating the system in a very special multi-layer live interactive system. Here you have the list of different form of brainwaves representation as a velocizer, converter, sonification, and all of them are used in different projects already mentioned. And then on the end, I'm talking about vacuum space, vacuum acoustic space in my piece Nothing, from 2010, which is a case of vanishing space. So here you have you should dive into the silent space. In fact, it's not silent. It's based on very high frequency, which are not really audible, but they are spanning a concept of acoustic vacuum. That's all what I have for now. You have my website here on the end, so when you have any question, please start and do not hesitate to ask me. I'm available easily on the web, on Facebook, and on other services. All the best. Thank you very much for your attention. This is funny because okay.
Thank you very much to Marek Koloniewski. I'm Andrea Agostini. I'm chairing this session. So thanks a lot for this inspiring presentation. I especially like when I see that there is a sort of a triangle between technological research and theoretical reflection and artistic practice and creation. So thank you. That was really, really inspiring. There have been a few questions here. I have a few too, but let's start from what is Can you hear me? Yes, I guess so.
I hear you
Yes.
very well.
Okay, perfect.
Mm-hmm.
So let's see a few questions. There was one from Federico Fontana, to which you partly answered in the chat, but perhaps you might want to elaborate a bit on this. So it's about the potential and possibility of creating a vertical soundscape, so either physical or electronic.
Okay, so in fact, there was, of course, a small misunderstanding because I think that I skipped one extremely important item and element of the project. So, in fact, in each room, there are two people. One is a musician in the window playing its part. I, of course, also skipped all explanation how the project should be arranged and built up because that's another story. But I try to make as short as possible. But in fact, I missed the very important element. And the second person is near the entrance door, near the light switch. So when the musician plays his part, his sequence, the part of the score, the second person switches total darkness city. The people are outside the building. They watch the front wall of the building. And when they listen to the orchestra playing, they also see the light orchestration. You understand? That's the concept. So try to imagine the Bolero by Ravel. We start from the window, from a single window, but on the end, all the front wall is lighting, is full of light. So this is the concept. But in fact, I was considering a different repertoire. In my mind, I was thinking to start up from Fireworks by Handel on the beginning,
okay,
and with the fires on the roof of the building. But then the topophonic pieces, which includes the space element in the orchestration. You know, there are several pieces.
Yes.
There's a space dialogue between the instruments according to the location. We have the classical location, but with the contemporary repertoire, it's not really regular. So that's the second point. But the most interesting project was to start from the light score. Try to imagine you want to write a letter A on this building. So you indicate in the score what instruments and when they should start playing. So I built up the score without notes, just with the graphics, with the visuals I want to express, and then later we are composing the music. So that's the concept inside the vertical orchestra.
I see. Yes, that's fascinating. And actually, I was wondering always about the score. If you consider, since I understand that this is an utopian project, so you never actually got to realize it, or did you?
No, I was very close. In 2008, we have the 120 years anniversary of our Academy of Music in Krakow, and our academic orchestra was involved in the project. But from technical problems, I gave up. That was the right word, because we're close. But then I said, well, it's too risky.
I see.
To make a bet, performance. And
yes, I was actually wondering if you had considered the possibility of creating some sort of written delay lines in the score so as to recreate in a way what a wavefield synthesis system does, which of course is utopian unless you have some sort of very strict metronomic track the musicians should follow.
Well, in the project we had two conductors involved, and the whole concept was on the way to be prepared in a regular concert hall with the musicians on the last 2 days with the headphones, wireless headphones, with one conductor, just a regular conductor, while the second one was a metronome conductor. So the person was just involved to control the system, to distribute this with all those offsets and delays, in the right way. Because on the end, the orchestra, the plan was that the orchestra moving to the rooms, and they are separated. They don't see each other. Also, the role of the conductor is quite spectacular because, in fact, I thought about him to be lifted in this open space in front of the building, you know, on the level of the second floor. We have 6 floors of the building. So the idea was that it's in the middle of the building, in front of the building, you know, watching and conducting. But in fact, it was conducting also with the headphones and with a click track. So
Yes.
that was the idea, that there are, in fact, each of them are just following a metronome, a click track, prepared
I see.
all
Yes.
the rubatos and all those offsets. So of
That's
course,
clear.
right, that it's a little bit risky, utopic, but the starting point was to put the third dimension. So my idea was, when you watch in the Philharmonic Hall to the orchestra, I've got this feeling I would like to lift them in the vertical position, you know, like
Sure. Yes, it's fascinating.
there, and then to get this third dimension, the vertical dimension, to hear the sound moving up and down. So that was mainly the idea. And following certain parameters with wave field synthesis. I was in the technical university in Berlin and checking the system. So that was just the inspiration. But moving from, well, like a spatial composition and many other things, coming from the technical invention and then landing up back to more traditional means and turning a little bit the orchestra to be a special vertical orchestra.
This is very clear. I would like to ask you another question, always taken from our YouTube chat. This is from Andrea Valle. He asks, and I was about to ask the same exact question. Can you elaborate on the Chris Cutler collaboration? I'm very curious. So yes, he's like one of the greatest drummers alive, and I'm very envious of this collaboration.
Well, so we know each other very long, and we're cooperating in many cases. His book was translated to Polish, and well, in the 80s I was also starting up with several people experimental rock scene in Poland, like other freight train group. So that was very close to me, you know, the approach and to open this space. But in fact, the collaboration was a part of our 5 big project in a 100th anniversary of Poland celebration, and we were Polish artists were inviting international artists for single projects. So I talked with Chris and I said, well, this is the moment when I'm using a brainwave, you know, monitoring feedback system. So I have an idea that when we are inside the space, you are controlling one virtual hemisphere above us, and I'm controlling another one. So the space is in form of 2 hemispheres, and we in fact show what's going on in our heads, you know, while we are performing live, interconnected. So that was the idea. Well, we have a lot of recordings from the world premiere in Lviv in Ukraine, October 20. And we were on the way to perform recently, but of course it was postponed. We don't know the date. The beginning of August is also fixed. I think we are going to Milano in autumn, but it's also not confirmed.
Okay. Well, I hope so. I hope so. I will definitely come to check you out, and I guess this is the same for most of my friends and colleagues here in Torino. Okay, so thank you very much. I don't know if we have any other...
Waiting.
Sorry?
The project is ready, is waiting with 2 other artists responsible of ambisonic, you know, multi-channel space. Also concerned, I'm using very strange devices, rotating Bluetooth speakers, you know, rotating over the space. The same way Chris is using a lot of objects, and this is really like from a very miniature, small things to be processed and amplified on a larger scale. But what is most important, the laser and video projection, which is above us. It's spinning like a network around.
Okay, so thank you very much. I think we are running out of time. I don't see any other questions. So thank you. It's been a great honor, and I hope to see you soon in Milano.
Thank you very much.
Goodbye. Thank you.
I keep finger crossed. I stay
Yeah,
out you because now I'm here. Thank you very much. Bye bye.
Thank you. Goodbye.
Hello, my name is Sylvan Willemsen, and today I'll be presenting for you our paper titled DigiDrum, a haptic-based VRMI and a case study, written by myself, Anka Simona Horvath, and Maro Naskimben. So first I'll start with a brief introduction of our project, then I'll go into DigiDrum itself, our instrument, its design and a system overview. Then I'll go into a case study that we did with this instrument, where based on a research question we performed an experiment of which I will present the results and discuss these, and finally I'll end with some conclusions and insights to future work. So first of all, what is a VRMI? So this stands for a virtual reality musical instrument, which is a virtual musical instrument, or VMI, which is a software simulation of an instrument or an extension of an existing instrument, but with an added visual component, which is mostly given by virtual reality in this case. Then our instrument, DigiDrum, is a enhanced drum, or more specifically darbuka, as you can see here on the right. And I will now go more into detail how we enhanced the darbuka. So first of all, we see here a diagram of a user interacting with the drum. We have a physical drum, the darbuka, which we augmented with a haptuator or vibrotactile transducer or motor on the inside of the drum membrane, which we can then trigger with a physical model of a membrane or a simulated membrane, which I'll go into detail a bit later. Then on top of this we have a virtual drum in virtual reality, which the user sees through their head-mounted display, which in our case is an Oculus Rift. And this virtual drum is aligned with the physical drum, so the user plays both of these drums at the same time. Then for control of this virtual drum, which in turn will trigger the physical model, we use the leap motion, which we mount at the front of the head-mounted display. So it sees the hands from above, and the leap motion it contains infrared cameras that can accurately perform hand tracking. So we use this for control. So starting with the user, there are three modalities or senses that we are interested in, which are the visuals, the audio, and the haptic modalities, which we provide to the user through the head-mounted display for the visuals, soundproof headphones for the audio, and the darbuka drum for the haptics. And as mentioned before, this drum has a vibrotactile motor attached to it. Then on the other hand, we have the PC, which the user interacts with using the leap motion, where their hands are tracked by this and the leap motion sends data to the PC. Then the PC runs a Unity scene, Unity being a software with which you can make virtual reality applications. And this triggers the Unity scene to trigger the physical model, which then in turn sends the output of itself to both the haptuator and the soundproof headphones. and now you might be able to see why we use soundproof headphones. It's because when the motor starts vibrating on the membrane, this will also create sound, and we wanted these two modalities to be separately controlled. So the vibrotactile motor will only give haptics, and the headphones will only give the audio to the user. And finally, we have our Unity scene sending data, visual data, to our head-mounted display. So let's take a brief closer look at the physical model. So normally we use partial differential equations to describe motion of different objects. And in the case of a rectangular stiff membrane, it's the following equation, where we have a state of the membrane described over 2 dimensions of space, x and y, and time t. And we have a 2D Laplacian operator, which is a second order derivative in 2 dimensions of space. So then we have a few parameters with which we can tune this model, such as material density, thickness, tension, etc. And if we then look back at what all these terms in this equation mean, it's that the acceleration of the state of the membrane at a certain location depends on the tension, the stiffness, and over time it damps out. So there's a few damping parameters there that can tune how fast this sound dies out. So then we have this VRMI, our DigiDrum, and we thought, well, how it would be interesting to make a case study of this, where we came up with the research question: can a user's perception of material stiffness in an enhanced drum membrane, or our DigiDrum, change by using auditory and haptic cues? So by changing basically parameters in the physical model, can we induce a different perception of material stiffness while the user interacts with it? So going back to this slide, you would think that the parameter we want to change is the stiffness of the membrane, but in a membrane itself there's normally a very low stiffness. If there's a high stiffness, it would sound more like a metal plate, for example. So this parameter, so D, is very tiny in this case. So in order to change the perception of stiffness, we thought about changing other parameters, which are tension and frequency independent damping. So we can tweak these parameters to hopefully induce a different sensation of stiffness. So some audio examples of this. First of all, we have our high tension and high damping setting. Then low tension and low damping, so the other extreme. Then low tension, high damping. And finally, we have high tension with low damping. We also have a medium setting for both of these parameters, tension and damping. And there are audio files available through a link in the paper, so I would like to refer you to that. So our hypothesis is that higher values for both tension and damping, so sound being damped more, will positively influence the perception of stiffness, and here tension being the more important factor. So this is what we hypothesize. So we performed an experiment with a twofold goal. First of all, to improve our virtual reality musical instrument, and secondly, to answer, of course, our research question, whether the perception of stiffness can change depending on these parameters. So we had 16 participants, of which 9 were experienced musicians, and this we define as more than 5 years of experience. So this is a picture of the setup of our experiment, where we can see a user interacting with the drum here, wearing a virtual reality headset and soundproof headphones. And the headset has the lead motion attached to the front so that it can track the user's movements. So the setup of the experiment was the following. Participants were asked to rate the stiffness of different cases on a 1 to 7 scale. And we had 9 cases, so high, low, medium tension, and high-low medium damping in all of these combinations. And of course, these were randomized between participants to avoid any biases. Then we had a questionnaire that asked them about hand ownership. So how much did you feel that your hands were your own? Secondly, when answering to the stiffness questions, what did you rely on? Was that either or visuals, audio, or haptics? They could also answer more of these. And what changed between the conditions, and the same answers were available to them. It's maybe important to note that the participants did not take off their headphones and head-mounted display while while answering to the stiffness questions in between. So they would just give a rating when they are done with the case, and we would put the next case on for them without them having to take off their equipment. And finally, we have observation that we did during the experiment as a form of retrieving data. So our results should be considered preliminary because we have a small sample size and we have some issues with RVRMI and the interaction, which I'll get to soon. But what we did find in our results was that both tension and damping influenced the stiffness positively, which we previously hypothesized. But here, the damping was actually the more important factor. So as we can see here on the left, we have a scatter plot of all the cases and their ratings sorted first from damping and then to tension. And we can see a quasi-linear trend going up. And on the right, we can see the grouped scores, where from low to high, stiffness ratings would also go up. And with damping, this would be more than with tension. So from our questionnaire, we got answers that people were generally positive about hand ownership, so they felt like the hands were their own. So in this sense, this was good for the leap motion, as in we made a right decision in this sense to use that. Furthermore, participants relied mostly on audio when answering the questions related to stiffness. So it would be interesting to, in a future experiment, decouple the audio and haptics to see whether without audio people would actually focus more on the haptics and hopefully get some stiffness perception differences there. So from our observations, we saw that there was a misalignment between the physical and the virtual drum. So what we did for control is place the virtual drum slightly higher so that users, when interacting with the drum, would trigger the physical model. But what this meant in the eventual interaction was that users would interact with the air above it because they could already control the sound when not even touching the physical drum, which caused maybe a change in their answers for the haptics rather than the audio, or in favor of the audio rather than the haptics. And furthermore, because the leap motion was mounted on the head-mounted display, the hands weren't always tracked, as the user sometimes would look forward rather than down on their hands while interacting. So this was also an issue. And this could be solved by using a contact microphone, also on the inside of the drum membrane, for control. So a potential problem that could arise here is that the vibrotactile motor would, we would get a feedback loop where if the motor would vibrate, the contact microphone would pick it up. But there is a potential for just using the transient sound that we get from interacting with the drum as control. But this is for future investigation. So, for conclusions, preliminary results show that higher values for tension and damping increase the perception of stiffness, where damping is the more important factor. And for future work, we would like to improve the setup by adding a contact microphone, for example. First of all, for better interaction with the VRMI and to yield better results in a future experiment. And lastly, we would like to decouple the audio and haptics and see which of these modalities would be most important and whether people would actually focus more on the haptics when there wouldn't be any audio. So thank you for your attention. If you have any questions, feel free to email any of us, and I hope you have a nice virtual conference. Thanks.
Hello and greetings from Copenhagen. In this presentation, I would like to tell you about our work on the virtual tromba marina. For those of you who are not familiar with the tromba marina, it is a medieval musical instrument from Europe that has only one string, we call it a monochord, and is played with a bow. Unlike a violin or a guitar where the user frets the string all the way down on the neck, the tromba marina player has to dampen the string vibration at harmonic points. This results in a unique playing position with the bowing hand being closest to the nut and the pitch selecting hand being closest to the bridge. The instrument can be played both from a sitting or from a standing position. The sound producing mechanism revolves around this uniquely shaped bridge that is at rest, barely touching the body. Therefore, when the string starts vibrating, the bridge starts rattling and hitting the body, creating this trumpet-like timbre. This is where the name tromba marina comes from. Our tromba marina looks nothing like the original one because it is a multisensory VR musical instrument. And here on the right you see my colleague Sylvain and the co-author playing the instrument through our prototyping phases. One of the key elements of our instrument is this sensible haptic omni device, which is a 6 degrees of freedom tracking and 3 degrees of freedom haptic device. So axis is labeled with A, produce feedback, and axis is labeled with B, only track. When it comes to the VR environment, we're using the Oculus Rift platform with the headset and its 2 controllers. The sound is produced by a physically model engine written by Sylvain, and I would like you to check out his presentation and his paper that is also part of this SMC 2020, where he describes in detail how the physical modeling works. But for all general purpose, in our application, we're using 3 parameters: bow velocity, bow position, and bow pressure to control the engine. These parameters are captured with the sensible haptic omni. We're using Unity 3D as a glue to combine all these systems, where we produce visuals, we generate the audio. The physical modeling engine has been exported as a Unity native audio plugin, therefore it runs smooth. The haptics are controlled by Unity as well, and of course we're tracking everything in it. If we put those 2 instruments side by side, we see that they have some differences, of course, but some commonalities as well, like the bowing position and the playing posture. When it comes to controlling the instrument, we're using both Oculus controllers and the haptic omni. The haptic omni is used to track the bowing gesture. If you imagine the user holding the bow around point B3 and performing a bowing motion, this is tracked by the omni, and of course it provides feedback as well. When it comes to the pitch, we're not using the harmonic damping as in the real instrument. Instead, we're providing the users with 2 options: a discrete harmonic selection with buttons X and Y for up and down, and fine control that glides position in between those harmonics. Now I would like to talk about our evaluation. We performed an investigative study that has 2 goals. One is to evaluate the general experience of bowing in a VR environment using haptic feedback and accurate physical modeling sound engine. And the second is to evaluate the playability of a VR boat monochord. For this we had 14 participants, 12 male, 2 females. All of them were musicians. It was a prerequisite for us that they are musicians. And the evaluation was split in 2 phases. Phase number 1, the participants were encouraged to experiment at their own will and tried to discover the instrument in their own tempo. When phase 1 was concluded, we played the participants a recording of us performing on the instrument. This was a practiced piece that had a musical element, and it was a bit more elaborate than what they would have discovered in 15 minutes of trying. We hoped that by showing what is possible with the instrument, they're gonna feel inspired to try to replicate it or to create something similar on their own. This happened in phase 2, where they again had no indications except that they were supposed to explore the instrument at their own will. The whole evaluation took about 30 minutes per participant. We used 4 data gathering methods: the Think Aloud protocol, observations, questionnaire, which was a modified usability metric for user experience, and everything concluded with a short interview. Now I'm going to present you the results, starting with a quantitative one. On the top of the list is that the instrument was easy to understand, but is difficult to play. And this is something that satisfies us, because most instruments fall in this category, like a piano or a guitar. And the instrument experience was overall satisfactory, and this is something that we obtained from quantitative evaluation only for now. The haptic feedback is reported as realistic and natural, and the sound engine provides a high level of command, which means that the mapping that we did was satisfactory both in terms of the haptic, the audio, and the visuals. When it comes to the qualitative results, we get a similar positive overall impression. The first thing that is worth mentioning is that higher harmonics prove difficult to play. And this is something that is encountered in the physical instrument as well. The higher the harmonics that the player intends to perform, the more difficult it is. As you can imagine, the string becomes shorter and shorter, therefore the energy distribution all the way down to the bridge needs to be very efficient. When it comes to the sound, the users preferred the lower pitches. Some of them even said that the open string sounds the best. And we found out through our observation, through Think Aloud, and especially through interviews, that it is hard to excite the rattling bridge. Again, this is something that is encountered in the real instrument, where it takes some sort of technicality to play the instrument correctly, as in to have the correct bowing pressure and bowing speed so the bridge rattles. When it comes to the pitch selecting methods, it's a very polarizing decision. People who liked the joystick hated the buttons, and people who liked the buttons hated the joysticks for various reasons, sometimes saying contradicting facts like the joystick is the more realistic or the button is the more realistic. The haptic feedback has been also reported as satisfactory, with words as great, wow is impressive, and this is something that encourages us to continue our research in the haptic feedback VR instruments. And overall, it was a consensus that it is hard to play. The most advanced participants managed to play simple melodies like Twinkle Twinkle Little Star or Mary Had a Little Lamb, which is a popular choice apparently. Looking back, this Think Aloud protocol that we used might not be the best suited for a musical playing application, because it is well known that playing an instrument and speaking provide a similar cognitive load to the brain, therefore one might not be able to perform both of them at the same time. And of course, we only had 14 participants, which is a small sample size. The conclusions that we got through the questionnaire cannot be generalized to the large audience, but they are only used to reinforce the findings from the qualitative evaluation. Overall, the instrument is satisfying, and it provides a satisfying experience, both to the players, but also to us in terms of achieving our goals of designing a VR bowed monochord. We conclude that this instrument is having a high virtuosity level, because in 30 minutes that participants started from discovering how to play to performing very simple melodies in a sketchy way. But we see that with a lot of practice, and it's something that they told us as well, they could become better and master it. And a very interesting thing, and something that is great for us, is that modalities reinforce each other. And people reported that it was great to be able to see and to hear, but especially to feel how the instrument behaves, and this enhances the experience. This is all from me. In the end, I will play a clip that shows how the instrument sounds like, and if you have any questions regarding this or whatever we do in the Multisensory Experience Lab, don't hesitate to contact us. Thank you.
Okay. Thanks everybody for attending the session on physical modeling number 2 with audio haptic interactions. It's Federico Fontana here, University of Udine. I'm talking from a room of my home, so also children are around. So, but I cannot close the door, otherwise the Wi-Fi signal goes down. But there are several questions here, so I don't want to take too much time. And start immediately from the list, and especially concerning the first presentation, there are several questions, and I think perhaps I would start from the most important, that is probably related with the actuation, and I say audio and haptic tactile actuation, and even linking to the questions related in the thread to presentation number 2. So would you, Sylvain, please elaborate a bit? You can also look at the questions on your own, and summarize and elaborate a bit on this thing that is, I think it's one core part of your system, and the pros and cons that your choice brings along.
Yeah, so maybe to summarize, the way we built the setup is that we have the drum with a actuator on the inside, and then soundproof headphones to decouple the audio and the haptics as such, so that you don't hear anything from the drum membrane itself, but just from the headphones. And the sound that is sent to the headphones, or both the headphones and the actuator, is both the same physical model. So that is the way it works. So we try to decouple the sound and the haptics, and maybe, as I said, also in future work, we want to see whether if we can send different haptics than the sound, or different sound than the haptics, and see which modality contributes more to the perception of stiffness in this case.
Yeah, thanks. And some questions are about the precision in relation also with the experiment. So also in my own, I feel that probably the sense of stiffness that you were able to simulate with your tool might be biased by maybe possible delays or jitter, simply the way that the visual system acquires the gestures, and then the rest of the system renders the feedback. So what's your opinion on the possible bias of these components to the outcome of the experiment, especially in relation with the questions that have been addressed about this problems?
So after performing the experiment, we figured that through the questionnaire, or through people saying their opinions about the setup, that the what's it called? The control was kind of off. So as I said, maybe in future work we want to include a contact microphone, for example, or maybe optical sensors. I was just reminded by Razvan that there is some state-of-the-art on optical sensors for drumming control, and that would measure the displacement of this of the membrane for control of maybe a physical model. But yeah, like either that or a contact microphone that would notice the transients of the hit of the user, rather than from the outside in with the lead motion having some delay issues and control issues. So there's definitely some future work in control and interactivity in our instrument. Yeah.
Okay, thanks. Then shortly there's a question from Martin van Waalstein. Hi, Martin. And about the shape of the surface. So
yeah, I saw that question. So we model a rectangular membrane rather than a circular one, And the reason is that with a circular membrane modeled with finite difference schemes or finite difference time domain methods, the explicit model, at least, is not very well behaved. So you will need to go to more complex models in order to get that right. And also, we found that the sound is fairly similar, or at least close enough to the sound of the drum membrane or any membrane for that matter. So maybe to get closer to the geometry of the membrane, we would maybe try an implicit scheme for the finite difference scheme, or maybe some other techniques, physical modeling techniques that are better for modeling circular membranes. But we didn't find the rectangularness of the membrane to be quite the issue, actually.
Okay. Then from Nicolas Castagne, could you elaborate a bit on the possible computational issues coming with model?
Yeah, so the model right now is only, I think, maximum 20 by 20 points. So that is very easily computable. I think in the implementation, we programmed it directly into Unity in C#. So there was no need for low-level C++ in this case. So in that sense, the model was very, very well suited for this real-time application. So we really got on interaction exactly the sound at that time rather than a delay there. So that was good.
Okay. Many thanks, Sylvain. Now we would move to Razvan, presentation number 2. And so we browse through. Oh, sorry, Claude. Maybe do you have a question here? Because I have to browse across the. Claude, do you have any question or no?
No, no. It was very interesting, but
okay.
I have some question with the technique point.
Okay. Thanks. So back to presentation number 2, and again, let me have a look. Again, Martin, Razvan, can you see his question? Was satisfactorily defined? Yeah. I think everybody can see the specific question.
So the question is, how was satisfactory defined? And I mentioned our presentation that we deemed the experience satisfactory, and it's not something that we measured it in any way, but we observed. We used the triangulation of data, and throughout our evaluation, we concluded that people reported that they were happy to some degree. So that is something that we define as satisfactory. We have not established a satisfactory criteria list that our instrument should fulfill to become satisfactory. So maybe that's something that we can look in the future. The next question is, how did we capture the participant developing technique? And again, we didn't we didn't have a goal in capturing their developing technique, but we have observed that they have started sucking pretty much and trying to figure out the affordances, which it's the next question, by themselves. We didn't give them any hints except the fact that you hold the instrument with a grip like a bow or like a bass bow, depending on how you want, and you move it horizontally. So this is the only instruction that the participants got, and they were expected to experiment at their own will, so kind of figure out the affordances by themselves. And how we captured their improvement is that they got from the point of not knowing how the instrument works to some of them being able to perform simple melodies or riffs, like Twinkle Twinkle Little Star, as I said, and Mary Had a Little Lamb, and one participant tried to do some very famous Mozart piece that you might think of. The success of it was debatable, but the fact that they attempted to perform these melodies indicates us that they have got enough confidence that they
they got to a point where they could play what they wanted to. So this is how we roughly measured their improvement on technique. But it also was a 30-minute experience, plus minus on average. It was 30 minutes, so it was not that much time they could improve.
Okay, so then I guess that there was basically no complaint from participants concerning the bowing range. This relates to the last question
Actually,
from Adhiram Dixit.
We did get complaints about the bowing range, but it was mostly because of our implementation. And this is something that I have to talk a bit about how this device works, because it's been designed to work accurately on minuscule gestures. Therefore, big ample movements are theoretically very well tracked, but they're gained. We have not modified the low-level implementation of the plugin for this. We have used it as is, and the movements are gained with a gaining coefficient that is not known to us. Therefore, the motion in real world does not correspond one-to-one to the motion in the virtual world. But we have not got any complaints regarding that. The only complaint that we got was that our implementation was more or less affording for half the bow movement. We tried to center the bow at the middle, the instrument at the center position of the haptic device. Therefore, the bow would be in the middle as well. So practically half of the bow, this half of the bow would be usable, but the other half of the bow would not, because this would not extend as much. Again, it was more of a visual cue. I think that people would have liked to be able to use the entire bow visually than a haptic cue. I don't think anyone noticed that it was a discrepancy between the real motion and the virtual representation of it.
Okay, thanks, Razvan. So now, even if this session is supposed to finish at 6:10, I would reserve some minutes for Claude. I mean, so we have the opportunity to talk even from remotely with one of the masters of the say audio haptic feedback in music. And so he mentioned 1993 as one year when he presented results, and I started to look at those results in 1995 when I was preparing my graduation thesis. So it's almost 30 years since that date. And the question that if there are no other questions in the case, please write them down immediately. Then I would ask Claude, where are we now? So if can you summarize what, in your opinion, are the milestones in auditory feedback in relation with haptics that have been achieved in these decades, and if any, because so I want to hear from you. Then what are the next milestones that we need to achieve that are yet to come?
Oh, yes, thank you for this very important question, but I am not sure that I can answer.
If you cannot answer, who can?
I can answer concerning my own evolution and how I feel it can take place in the uses. I think that the next, for me, I hope that the next step will be to have actually real-time and multisensory interaction near our laptop and our very domestic tools, And in parallel, I hope and I think that it is very possible that it will be possible to have it is what I call the nomadicity in my paper. That is a possibility to articulate both very performant, very accurate and performant system, and also very nomad, very transportable system. So this is what I would like. Now I am not sure that I can say what will be.
Okay, thanks. I mean, it's an important answer. I mean,
yes, thank you.
Yeah, okay. So I think the session is over with 1 minute delay. So if there are no more questions, then I will thank everybody once again for presenting and for participating. And so meet you at the evening concert or tomorrow morning with the next scientific session. And have a good evening wherever you are. And have a nice dinner, maybe not so social. But
Thank you very much.
bye-bye.
Okay, I'm popping up, and I'd like to thank you all for being here in this second long and fruitful day of the SMC conference. Now, the scientific program will start again tomorrow at 9 Central European Summer Time. So please don't go bed too late watching again the conference on YouTube because, well, it will remain there, so you will have time. And also remember that at 7 p.m. we have 10 acousmatic pieces in our music program. So we will be back to you in less than an hour with the music program. So this said, see you later and have a good break before the program, the music program.
Bye-bye.
El computador puede ayudarnos a componer música. El computador Hay muchas maneras distintas de obtener melodías, ritmos o armonías por medio de cálculos hechos por un computador. Pero no olvidemos que el computador no es sino una prolongación del ser humano, quien es, en definitiva, el que toma las grandes decisiones y da la orientación y significación de lo que con estos medios puede realizarse.
Yeah, yeah. Yeah. Ah, hi.
Sure.
Annoy. Yeah.
Ou peut-être n'est-ce qu'un fonderie? L'homme de ce Saraco, comme il s'en comporte entre lui et la trine, à l'ère de la mise au baquet, des repas une fois de plus engurgiteux. Où ça sent la merde? Ça c'est l'aide. Parce qu'il est mal construit. Il faut se décider à les mettre à nous pour écraser ces Je ne délire pas. Je ne suis pas. Je vous dire. Un malade. Parce qu'il est mal construit. Il faut se décider à le mettre à nous pour lui gratter cet animal. Dié et avec. Dié.
Ce qui est grave est que nous